Look up at the night sky on a clear evening, and you'll see a scattering of stars, pinpricks of light, in what seems like an endless, unchanging darkness. But what if I told you that darkness isn't static, that the universe isn't just expanding, but expanding unevenly, stretching in some places faster than others, as though some hidden hand were gently, mysteriously, tugging at the fabric of reality itself? This isn't science fiction. It's one of the most profound and puzzling discoveries in modern cosmology. For decades, we imagined the cosmos growing uniformly, like a perfectly smooth balloon inflating in all directions. But now, thanks to astonishingly precise observations, we know that's not the whole story. The universe has wrinkles, it has rhythms and irregularities that hint at deeper laws and perhaps even deeper questions than we ever thought to ask. This video is an invitation to explore that very mystery, why expansion isn't uniform, and what that might imply about the universe's hidden nature or even its intent. We're going to journey through space and time, from the afterglow of the Big Bang to the farthest edges of the observable cosmos. We'll examine how dark energy behaves differently in vast cosmic voids than it does within dense galaxy clusters. We'll consider whether quantum fluctuations from the earliest moments of creation set this unevenness in motion, and whether theories like the multiverse or cosmic inflation can help us make sense of it all. Most compelling of all, we'll ask whether these irregularities are random, or if they point towards something more deliberate, something almost like design. By the time we reach the end of our exploration, you won't just understand the science behind non-uniform expansion, you'll feel it. You'll see the cosmos not as a cold, empty expanse, but as a dynamic, evolving entity full of pattern, tension, and beauty. You'll appreciate why telescopes like Hubble, James Webb, and Euclid are racing to map these cosmic asymmetries, and why physicists and philosophers alike are captivated by what they might mean. So come with me, let's look closer, think deeper, and unravel one of the greatest mysteries of our time, a mystery written in the very expansion of the universe. To understand why the universe isn't expanding evenly, we have to rewind the clock all the way back to the very beginning, to the event we call the Big Bang. For a long time, the prevailing image was one of a perfectly smooth, incredibly hot and dense fireball that began to cool and stretch outward in every direction simultaneously. This idea of a uniform start is built on two foundational principles that cosmologists call homogeneity and isotropy. Homogeneity means the universe looks roughly the same at every point, no special location. Isotropy means it looks the same in every direction you look, no special axis. This assumption of a smooth, even cosmos was so central that it became a cornerstone of our main model of the universe, a pillar holding up our entire understanding of cosmic evolution. The strongest evidence for this initial smoothness comes from a faint glow that permeates all of space, the cosmic microwave background radiation. Think of this as the universe's baby picture, taken when it was just 380,000 years old. This afterglow from the Big Bang is astonishingly uniform, a nearly perfect blanket of microwaves with a temperature just a few degrees above absolute zero. But nearly is the most important word here. When we built satellites powerful enough to map this background radiation in exquisite detail, like the Planck and WMAP missions, they revealed something profound: tiny, tiny fluctuations. Minute variations in temperature on the scale of 1 part in 100,000. These are the anisotropies, the slight irregularities in the cosmic fabric. These tiny imperfections were anything but minor. They were the seeds of all structure we see in the universe today. Imagine a vast, perfectly flat and calm lake. Suddenly, you introduce the most minuscule ripples. Given enough time and the right conditions, those tiny ripples can evolve into powerful waves and complex patterns of interference. In the cosmic context, gravity is the force that amplifies those ripples. Slightly denser regions revealed by those faint temperature spots had slightly stronger gravity. Over billions of years, they pulled in more and more matter, eventually growing into the magnificent galaxies, galaxy clusters, and the vast filamentary web of dark matter that connects them. The emptier regions, meanwhile, evolved into immense cosmic voids. So the universe we see today, a breathtaking tapestry of brilliant clusters and immense dark voids, is a direct result of those initial microscopic flaws in the cosmic background. This sets the stage for our central mystery. We started with a model that assumed perfect smoothness, which logically led us to expect a perfectly smooth expansion. But if the matter isn't distributed evenly, why would the expansion be? The gravitational tug of war is different everywhere. It's like trying to inflate a balloon that has thick, rigid patches of rubber glued to its surface in some places and thin, stretchy patches in others. It's not going to expand in a simple, spherical way. The universe, it turns out, is not a perfect balloon. It's a complex, structured entity, and its expansion reflects that beautiful, complicated reality. But if those initial wrinkles in the cosmic fabric set the stage for an uneven universe, the plot truly thickened with the discovery of a mysterious new character in our cosmic story, dark energy. For a long time, we thought the expansion of the universe, set in motion by the Big Bang, was gradually slowing down thanks to the relentless pull of gravity. That all changed in the late 1990s when two independent teams of astronomers, one led by Saul Perlmutter and another by Adam Rees and Brian Schmidt, made a shocking observation. By studying distant supernova, they found that the expansion isn't slowing at all, it's speeding up. Something was overpowering gravity, pushing galaxies apart faster and faster. That something earned the name dark energy, and it remains one of the greatest enigmas in all of physics. The simplest explanation, the one Einstein himself once proposed and then discarded, is the cosmological constant. This idea treats dark energy as a uniform, unchanging property of empty space itself, a constant energy density that exerts a negative pressure, causing the acceleration. It's an elegant idea, but it comes with a huge problem. As Adam Rees has pointed out, the value we measure for this constant is astronomically small compared to what particle physics predicts it should be, creating what many call the worst theoretical prediction in the history of science. This discrepancy alone suggests our understanding is incomplete, but there's an even bigger issue. This model assumes dark energy is perfectly smooth and uniform everywhere. What if it isn't? This is where the plot gets really intriguing. Imagine dark energy not as a constant, uniform field, but more like an invisible, ethereal wind blowing through the cosmos. In some regions of space, this wind might gust fiercely, while in others, it's little more than a gentle breeze. This isn't just a fanciful idea. Observations are starting to hint that it might be true. Large-scale galaxy surveys mapping the universe in 3 dimensions have begun to reveal subtle variations in how fast different regions are expanding. Some vast cosmic voids, those enormous empty spaces between the galactic filaments, seem to be stretching faster than our models predict, as if dark energy is more potent there. In denser regions like our local supercluster of galaxies, the gravitational glue might be resisting that push more effectively, creating a slower local expansion rate. This is the prime evidence that dark energy's influence might not be uniform after all. This has led physicists to propose more dynamic and exotic theories than a simple constant. One of the leading candidates is called quintessence. Think of quintessence not as a static force, but as a kind of energy field that evolves and changes over time. It could have fluctuations in its density, much like the early universe had fluctuations in matter density. If that's the case, then dark energy could indeed be stronger in some places and weaker in others, directly accounting for the uneven expansion we're beginning to detect. Saul Perlmutter has often emphasized that the key to solving this mystery is more data, and that we have to be open to the possibility that dark energy is something far more complex and interesting than we initially imagined. So, what does this mean for the idea of a universe with intent? If dark energy is simply a constant, a fundamental number etched into the laws of physics, its uniformity could be seen as a sign of a cold, impersonal cosmos. But if it's something like quintessence, a dynamic, fluctuating field that varies from place to place, it opens the door to a much more textured and nuanced reality. It suggests that the force shaping the entire fate of the cosmos has a personality, with hills and valleys of influence. This doesn't necessarily imply a conscious designer, but it does point toward a universe of profound complexity, where the rules might not be as simple and universal as we once dreamed. The behavior of this mysterious force could be the key to understanding whether the uneven expansion is a random byproduct of underlying physics or a feature woven into the very fabric of existence. But to truly appreciate how this plays out, we need to move from the abstract force of dark energy to the tangible architecture of the cosmos itself. If you could step back and view the universe on the grandest possible scale, you wouldn't see a random scattering of galaxies. Instead, you'd witness an immense, intricate cosmic web, a vast network of glittering galaxy clusters connected by long, faint filaments of gas and dark matter, all separated by enormous, almost empty regions known as cosmic voids. This is the large-scale structure of the universe, and it's the most dramatic proof that matter is anything but evenly distributed. It's a cosmic metropolis with bustling urban centers, sprawling suburbs, and unimaginably vast, empty deserts. This magnificent structure didn't appear overnight. It's the end result of a billions of years-long gravitational dance that began with those tiny seeds of imperfection we saw in the cosmic microwave background. Slightly denser regions, powered by the gravitational pull of their unseen dark matter content, began to pull in more and more material from their surroundings. Over eons, these regions grew into dense nodes, the great galaxy clusters, each containing thousands of galaxies. The matter between these nodes was stretched into the wispy filaments of the cosmic web, while the areas that started out with less material were gradually emptied out, evolving into the vast voids. Projects like the Sloan Digital Sky Survey have painstakingly mapped this structure by measuring the positions and redshifts of millions of galaxies, giving us a three-dimensional atlas of our cosmic neighborhood that reveals this stunning web-like pattern in incredible detail. And this uneven distribution of matter creates an equally uneven landscape for cosmic expansion. Think of it like this: gravity is the brake and dark energy is the accelerator. In the dense urban centers of the universe, the galaxy clusters and filaments, gravity is incredibly strong. All that mass is pulling inward, fiercely resisting the outward push of dark energy. The expansion still happens here, but it's significantly slowed, like a car trying to accelerate up a steep hill. Now, travel out into the cosmic voids, those immense deserts that can be hundreds of millions of light years across and contain almost no galaxies. Here, there is very little matter, which means there's very little gravitational pull to counteract dark energy. In these near-empty regions, dark energy has its foot firmly on the accelerator with almost nothing holding it back. The void doesn't just expand, it expands faster than the universe's average rate. This isn't just theoretical. Astronomers have directly measured this effect. By studying the motions of galaxies on the edges of voids, they can see them being pushed apart by this accelerated expansion. The void itself acts like a bubble of faster-growing space, stretching the fabric of the cosmos within it more rapidly than in the denser regions around it. This creates a patchwork universe, a cosmos where the rate of expansion isn't dictated by a single, universal constant, but is instead a local phenomenon, deeply connected to the density of your immediate environment. The universe isn't expanding in one single, monotonous way. It's a symphony of different tempos, with voids expanding in a rapid allegro and dense clusters holding a much slower, more gravitationally bound adagio. This tangible, observable evidence moves the concept of non-uniform expansion from a theoretical curiosity to a concrete feature of our reality, showing us a dynamic and textured cosmos where location truly determines your cosmic destiny. So we have this cosmic web, a universe of varying densities and expansion rates, but that just pushes our question further back in time. Where did the initial seeds for this intricate structure come from? To find that answer, we have to venture into the most fleeting moments after the Big Bang, to a concept that is both spectacular and mind-bending: cosmic inflation. Proposed in the early 1980s by physicist Alan Guth, inflation is the idea that the universe underwent a period of exponentially rapid expansion, ballooning from a subatomic speck to something macroscopic in a fraction of a second. This theory elegantly solves several major puzzles, like why the universe appears so flat and uniform on the largest scales. But within this incredibly brief and violent period of smoothing lies the very origin of cosmic roughness. During this inflationary expansion, the universe wasn't a perfectly calm, empty space. Thanks to the principles of quantum mechanics, it was a seething, bubbling foam of energy. At these unimaginably small scales, the Heisenberg uncertainty principle tells us that empty space is never truly empty. It's alive with quantum fluctuations. Tiny particles and antiparticles constantly pop into and out of existence, borrowing energy from the vacuum for the briefest of moments. Now, imagine this quantum fizz happening during inflation. A tiny fluctuation, a minute difference in energy density, would appear for an instant, but in that same instant, the inflationary expansion would stretch that tiny region of space to an astronomical size. What was a quantum blur smaller than a proton would, in the blink of an eye, be inflated to a scale of many light years. This process happened everywhere, all at once, imprinting these quantum ripples onto the fabric of the newborn universe. These stretched-out quantum fluctuations became the ultimate blueprints for everything that followed. They were the slight over-densities and under-densities that, once inflation ended and the universe settled into a more sedate expansion, served as the gravitational seeds for structure formation. The slightly denser regions had a bit more gravitational pull, eventually attracting dark matter and gas to form galaxies and clusters. The less dense regions evolved into the great cosmic voids. The cosmic microwave background, that baby picture of the universe, is essentially a snapshot of these inflation-born ripples frozen in time, and the delicate patterns we see in it match the predictions of inflationary theory with remarkable precision. As Andre Linde, another key architect of inflation theory, has described it, this process is like taking a tiny piece of canvas with the most microscopic, random imperfections and stretching it into a vast tapestry. The pattern is magnified, but its origin is in those initial quantum-scale wrinkles. This leads us to an even more profound implication of inflation. the possibility that our entire universe is just one bubble in a much vaster and perhaps infinite cosmic foam. This is the theory of eternal inflation. The idea is that once inflation starts, it may never truly stop everywhere at once. Instead, the inflationary energy can decay in certain regions, each one forming a distinct bubble universe with its own Big Bang and its own laws of physics, while the space between these bubbles continues to inflate eternally. In this multiverse scenario, the specific properties of our universe, the strength of its forces, the mass of its particles, even the nature of its dark energy, might be just one random outcome among a near infinite number of possibilities. In this breathtaking view, the non-uniform expansion we're beginning to measure in our own cosmic backyard might not be an anomaly at all. It could be a local signature, a natural consequence of how our particular bubble universe formed and cooled within a much grander, eternally inflating meta-universe. Perhaps the variations we see are echoes of the chaotic process that gave birth to our local spacetime. This doesn't just connect early universe physics to modern observations. It suggests that the initial conditions of our existence were not a single, definitive event, but part of an ongoing, perhaps infinite, creative process. The irregularities we trace in the night sky might be our first glimpse into a reality far larger and more strange than we ever imagined. So how do we actually know any of this? How do we move from theoretical possibility to confident observation? The answer lies in the incredible precision of our cosmic cartography, a mapping project carried out by some of the most sophisticated machines humanity has ever built. Telescopes like Planck, WMAP, and Hubble aren't just taking pretty pictures. They are forensic instruments collecting light that has traveled across billions of years to deliver evidence about the fundamental nature of reality. And the evidence they are gathering is increasingly pointing toward a universe that is not expanding at the same rate in all directions. Let's start with the Hubble constant, the number that represents the current expansion rate of the universe. For decades, the goal was to pin down a single, precise value for this number. But what if the value depends on where you look? This is the tantalizing suggestion from several lines of inquiry. Astronomers use what are called standard candles to measure cosmic distances. A standard candle is an object whose intrinsic brightness we know, like a specific type of stellar explosion called a type Ia supernova. By measuring how bright it appears to us, we can calculate how far away it is. Combine that distance with a measurement of the galaxy's redshift, how much its light has been stretched by the expansion of the universe, and you can calculate the expansion rate. When teams began making these measurements in different parts of the sky, some began to report a curious signal, a dipole anisotropy. This is a fancy way of saying the expansion seems to be ever so slightly faster in one general direction and slower in the opposite direction, as if we are moving through a cosmos that isn't perfectly uniform. But supernovae aren't the only tool in the toolbox. Another powerful method uses what are called baryon acoustic oscillations. This mouthful refers to a permanent frozen ripple in the distribution of galaxies. In the very early universe, pressure waves traveled through the hot plasma, much like sound waves travel through air. When the universe cooled enough for atoms to form, these waves froze in place, leaving a characteristic scale, a preferred distance between galaxies. By measuring this standard ruler in the large-scale structure of the universe, scientists can also derive the expansion rate at different epochs. When they combine this with the pristine view of the infant universe from the Planck satellite, which measures the Hubble constant from the cosmic microwave background, a major conflict emerges. The early universe method gives one value for the expansion rate, while the late universe method, using supernova and other local measurements, gives a consistently higher value. This discrepancy is known as the Hubble tension. and it's one of the most significant puzzles in modern cosmology. While some scientists work to resolve this tension by looking for errors or new physics, others are investigating a more radical explanation, that the tension itself is evidence that the expansion rate isn't uniform. Perhaps the local measurements are higher because our region of the universe is, for some reason, expanding faster than the cosmic average. The data from these telescopes is so precise that we can now create maps of the Hubble constant across the sky. While the variations are subtle, they are persistent, and they align with the underlying distribution of matter and the vast cosmic voids. The emptier regions do seem to be stretching faster, just as our theories predicted. This isn't just a single anomalous measurement. It's a consistent story being told by multiple independent instruments looking at the universe in completely different ways. From the afterglow of the Big Bang to the death throes of distant stars, the message is the same. The cosmos is not expanding evenly. The data is on the table, and it is compelling us to ask not if the universe is anisotropic, but why. This brings us to the heart of the modern cosmological crisis, a puzzle so persistent and so puzzling that it has the entire field of astronomy re-evaluating its most fundamental assumptions. It's called the Hubble tension, and at its core is a simple, unsettling question. How fast is the universe actually expanding? You would think that after a century of measurement, we'd have a single, agreed-upon number for the Hubble constant. But we don't. Instead, we have two of the most precise measurement techniques in the history of science, honed over decades, giving us two different, stubbornly incompatible answers. It's as if we had two of the world's most accurate clocks, built by master craftsmen, and one is consistently ticking faster than the other. This isn't a small margin of error. It's a significant and growing discrepancy that points to a fundamental flaw in our understanding of the cosmos. On one side, we have what's known as the early universe measurement. This method uses the exquisitely detailed map of the cosmic microwave background provided by the Planck satellite. By analyzing the subtle patterns in this primordial light, the size of the ripples, and how they correspond to the distribution of matter, cosmologists can run the cosmic film backwards to the Big Bang and then forwards again within the standard model of cosmology. This process predicts what the expansion rate should be today. It's an incredibly powerful and self-consistent approach, and it gives us a Hubble constant of about 67.4 kilometers per second per megaparsec. This means that for every megaparsec of distance, a mind-boggling 3.26 million light-years, a galaxy is moving away from us at 67.4 kilometers per second faster. On the other side, we have the late universe measurements. This is the direct, local approach championed by astronomers like Nobel laureate Adam Rees and his team using the Hubble Space Telescope. They look at the present-day universe, identifying what are called standard candles, objects whose true, intrinsic brightness we know. The gold standard here are Type Ia supernova, the spectacular explosions of white dwarf stars. Because we know how bright they should be, we can measure how bright they appear to be and precisely calculate their distance. By then measuring the redshift of their host galaxies, how much their light is stretched by the expansion of space, we get a direct local measurement of the expansion rate. This method, along with other local techniques, consistently gives a higher value, around 73 kilometers per second per megaparsec. That's a difference of nearly 6 kilometers per second. It might not sound like much, but over the vast scales of the cosmos, this discrepancy adds up to a massive uncertainty about the universe's age, its size, and its ultimate fate. The scientific community is deeply divided on what this means. As renowned cosmologist Wendy Friedman of the University of Chicago has noted, the teams have checked and rechecked their work for years, searching for any hidden systematic error. any tiny miscalibration that could explain the gap. But so far, nothing has emerged. The measurements just won't agree. George Efstathiou, a key scientist on the Planck team, has expressed both frustration and fascination, stating that if this tension is real and not an error, it means we are missing something crucial in our standard model of physics. This vigorous, healthy debate is science at its best, a clash of data that forces everyone to think harder. So what are the possible resolutions? The first, and in some ways least exciting, possibility is that there is a subtle, overlooked error in one of the measurement chains. Perhaps our understanding of the physics of supernova is imperfect, or there's a tiny bias in how we measure cosmic distances that we haven't yet accounted for. Teams around the world are working tirelessly to rule this out with new data from the James Webb Space Telescope, which is providing even sharper views of these standard candles. The second and far more thrilling possibility is that we are seeing the first compelling evidence for new physics. The standard model of cosmology, known as lambda CDM, is incredibly successful. But the Hubble tension might be its first major crack. Perhaps dark energy isn't a constant but is evolving over time, becoming stronger and accelerating the expansion more than our models predicted. Maybe dark matter has properties we haven't yet discovered, interacting in strange ways that affect the expansion rate. Or perhaps there is a new, unknown particle or field influencing the cosmos. Then there's the third possibility, the one that ties directly into our main theme, that the Hubble tension is evidence that the expansion isn't uniform. What if the local measurements are higher because our region of the universe, a volume encompassing billions of light years, is simply in a faster expanding bubble? We already know we reside in a relative underdensity, a cosmic void on a grand scale. If dark energy is more effective in these emptier regions, then our local measurement of the Hubble constant wouldn't be the one true universal value, it would just be our local reading. The early universe measurement from the CMB would give us the true average, while we are living in a specific neighborhood where the expansion is slightly amped up. This wouldn't just solve the Hubble tension, it would fundamentally change our cosmic address, suggesting we live in a special, atypical part of a far more complex and anisotropic cosmos than we ever dreamed. So if the Hubble tension is indeed a sign that we're living in a cosmic outlier, a faster expanding bubble within a much larger and more varied reality, then we are inevitably led to one of the most profound and mind-expanding ideas in all of science, the multiverse. This concept pushes far beyond the idea of a single, unified cosmos and suggests that our entire universe, with its hundreds of billions of galaxies and its specific laws of physics, might be just one single bubble in an infinite, frothing sea of other universes, each with its own unique properties. In such a breathtaking scenario, the non-uniform expansion we're struggling to understand wouldn't be a mysterious feature of our universe's intent. It might simply be a local artifact, a completely random and accidental characteristic of our particular cosmic neighborhood. To understand how this could work, we return to the theory of cosmic inflation, but push it to its most extreme and logical conclusion. The original idea of inflation describes a brief, violent period of expansion that launched our universe. But what if that process never truly stopped? This is the theory of eternal inflation, championed by physicists like Andre Linde. The idea is that the inflating energy of the primordial universe, the thing that caused the Big Bang, continues to operate in the vast spaces between budding universes. In this eternal, metaphysical landscape, quantum fluctuations can cause the inflationary energy to decay in certain spots, each one sparking a localized Big Bang and forming a distinct, self-contained bubble universe. Our entire cosmos, from the farthest quasar to the closest star, would be contained within one such bubble. and crucially, the specific conditions of that bubble, the strength of its fundamental forces, the mass of its electrons, the nature of its dark energy, would be determined by the random details of how that particular bubble formed. Some bubbles might have laws of physics that allow for stars, planets, and life. Vastly more of them would be stillborn or barren, expanding into cold, empty voids or collapsing instantly back in on themselves. This is where the brilliant work of theorists like Max Tegmark and Brian Greene adds incredible depth. Tegmark's classification of multiverse levels helps us grasp the sheer scale of the possibility. A level 1 multiverse is simply our own infinite universe, where every possible configuration of matter eventually repeats itself in the vastness. But a level 2 multiverse is the inflationary kind, where different bubbles have genuinely different fundamental constants and physical laws. Brian Greene's work in string theory takes this even further, suggesting a vast landscape of possible universes, perhaps 10 to the 500 different possible configurations, each corresponding to a different way for the extra dimensions proposed by string theory to be curled up and compactified. In this unimaginably vast landscape, finding a universe with exactly our set of constants isn't a miracle. It's a statistical inevitability. We find ourselves in this particular universe with its specific expansion rate and its amount of dark energy, not because it was designed, but simply because it's one of the rare versions that could support conscious beings like us who are around to notice. This is the anthropic principle in action, not as an explanation, but as a selection effect. Now, apply this multiverse lens to our puzzle of non-uniform expansion. In this grand view, the slight anisotropies we measure, the variations in the Hubble constant, and even the stubborn Hubble tension itself could all be perfectly natural. Our bubble universe might simply be one that, by pure chance, ended up with a slightly lumpy distribution of dark energy or a minor asymmetry imprinted from its birth during eternal inflation. What we are measuring might not be the fundamental law of a single cosmos, but merely the local zoning laws of our particular cosmic suburb. The search for a single, universal reason for the expansion rate becomes almost beside the point. There is no single reason. There are countless reasons, each applying to a different universe in the infinite ensemble. The grand scheme isn't a design but a magnificent, purposeless, and unthinking proliferation of possibilities. Our universe isn't special or intended. It's just one possible outcome that happened to be compatible with our existence. This doesn't make the mystery any less profound, but it does reframe it entirely, transforming our quest from one of deciphering a cosmic blueprint to one of simply understanding the local bylaws of our own accidental and perhaps utterly average cosmic home. But if our universe is just one accidental bubble in a vast multiverse, a cosmic roll of the dice that happen to come up with the right numbers for life, then we are faced with a profound and deeply human question. Why do the numbers seem so perfectly arranged in our favor? This brings us to one of the most fascinating ideas at the intersection of cosmology and philosophy, the anthropic principle. Coined by astrophysicist Brandon Carter in the 1970s, the principle in its simplest form observes that the universe we observe must be compatible with the existence of observers. It seems like a tautology, a statement of the obvious, but its implications are staggering when you consider the exquisitely precise fine-tuning of the cosmos. Consider the force of dark energy, the very engine of our uneven expansion. The value of this force is bafflingly small. If it were just slightly stronger, the accelerated expansion would have begun so early in the universe's history that galaxies, stars, and planets would never have had time to form. The universe would have been ripped apart into a thin, cold, and lifeless haze of isolated particles. If it were significantly weaker, gravity would have dominated completely, causing the universe to collapse back in on itself in a big crunch long before life could evolve. We exist in a breathtakingly narrow window where the strength of dark energy allows for just the right amount of structure to form. The same is true for countless other constants: the strength of gravity, the mass of the proton, the exact properties of the carbon atom. Alter any one of them even minutely, and the universe becomes sterile. As physicist Leonard Susskind has pondered, this incredible fine-tuning demands an explanation. Is it merely a colossal, meaningless coincidence, or does it point toward something deeper? This is where the anthropic principle splits into two compelling interpretations. The weak anthropic principle is the more conservative scientific stance. It simply states that we must find ourselves in a region of the universe and at a time in its history that is capable of supporting life. It doesn't explain why such a region exists. It just acknowledges the selection bias that we can only observe conditions that allow for observers. In this view, the non-uniform expansion isn't a designed feature, it's a necessary byproduct. The vast, empty voids are expanding away rapidly, but that's precisely what allows for the existence of stable, slower expanding islands like our galaxy, where gravity can work its magic and forge the complex structures required for life. The irregularities aren't for a purpose. They are simply the environment in which we, by necessity, had to arise. The strong anthropic principle, however, takes a far more radical leap. It proposes that the universe must have properties that allow life to develop at some stage in its history. This version often veers into metaphysical territory, suggesting that the laws of physics and the initial conditions of the cosmos are somehow constrained by the requirement to produce conscious life. For some, this implies a form of teleology, that the universe is in some sense directed toward a goal, that there is an intent or a design woven into the fabric of reality. This doesn't necessarily mean a traditional deity, but it does open the door to the idea that consciousness is not a late arriving accident but a fundamental aspect of the cosmic scheme. The multiverse theory provides a powerful, if unsettling, resolution to this debate. It supports the weak anthropic principle on a grand scale. In an infinite multiverse, every possible value for every physical constant will be realized in some bubble universe. The vast, overwhelming majority of these universes will be stillborn or barren, but in a tiny, tiny fraction of them, the numbers will line up just right. We shouldn't be surprised to find ourselves in one of those rare, life-friendly universes. We couldn't possibly find ourselves anywhere else. The fine-tuning isn't evidence of design, it's evidence of a cosmic lottery with a near-infinite number of tickets. Our universe isn't special, it's just the one that worked. This perspective, championed by thinkers like Susskind in his work on the string theory landscape, uses the multiverse to drain the apparent fine-tuning of its mystical quality, explaining it through probability and sheer vastness. The question shifts from, why is our universe so perfectly tuned for life, to, what does it mean that we are the lucky winners in a draw of incomprehensible odds? The answer may be that it means nothing at all about intent, and everything about the staggering power of chance and selection in a reality of infinite possibilities. Yet if the seeds of all structure were planted by quantum randomness, we are left staring into a profound and deeply philosophical abyss. Does this inherent indeterminacy at the heart of physical reality rule out any notion of a grand design or cosmic intent? Or could it be that this randomness is not the absence of purpose, but rather the very mechanism through which a more complex, creative form of purpose operates? To grapple with this, we need to venture into the bizarre and counterintuitive world of quantum mechanics, a realm where certainty dissolves and probability reigns supreme. The entire edifice of this quantum unpredictability rests upon a cornerstone principle formulated by Werner Heisenberg in the 1920s, the uncertainty principle. In its most famous form, it tells us that we cannot simultaneously know both the exact position and the exact momentum of a subatomic particle. The more precisely you pin down one of these properties, the more wildly uncertain the other becomes. This isn't a limitation of our measuring equipment. It is a fundamental, inescapable feature of the universe itself. At its core, reality is fuzzy, not sharp. This inherent fuzziness leads directly to the phenomenon of vacuum fluctuations. We often think of a vacuum as pure, empty nothingness, but according to quantum field theory, the vacuum of space is a seething, bubbling sea of potential. Everywhere and at all times, pairs of virtual particles and antiparticles are spontaneously borrowing energy from the vacuum, flickering into existence for an unimaginably brief moment before annihilating each other and returning the energy. They are a transient rebellion against nothingness, a constant proof that empty space is alive with restless energy. Now cast your mind back to the theory of cosmic inflation. For a fleeting fraction of a second, the entire observable universe was smaller than one of these virtual particles. In that incredible moment, the quantum foam wasn't just a microscopic curiosity, it was the universe. And when the inflationary expansion happened, it didn't just stretch space, it stretched those quantum fluctuations, those tiny, random differences in energy density, and it blew them up to cosmic proportions. A virtual particle pair flickering into existence here instead of there, a tiny region of space with a minuscule bit more energy than its neighbor. These random quantum events were magnified into the density variations that would one day become entire galaxy clusters and vast cosmic voids. The largest structures we can observe were born from the smallest, most random events possible. This presents us with a monumental philosophical choice. On one hand, this seems like the ultimate argument for a purposeless, accidental universe. The distribution of galaxies, the very framework of the cosmic web, appears to be the end result of a colossal cosmic lottery, a random number generator operating at the dawn of time. There is no guiding hand, no blueprint, only the blind, uncaring roll of quantum dice. In this view, any appearance of design or fine-tuning is a classic example of the Anthropic principle. We just happen to live in a universe where the random outcomes were compatible with our existence. But there is another, more nuanced perspective. What if this quantum randomness is not the antithesis of design, but its essential ingredient? Consider an analogy from the natural world. Look at a magnificent, sprawling oak tree. Its exact shape, the specific placement of every branch, every twig, every leaf, is not predetermined in a rigid, mechanical blueprint. It is the result of countless random events. A gust of wind bending a sapling here, a period of drought-stunting growth there, a chance encounter with an animal breaking a branch. The final form is unpredictable and unique, emerging from a cascade of random occurrences, and yet nobody would look at that oak tree and declare it an accident. It is clearly the expression of an underlying design, the DNA of an oak, working through randomness and environmental interaction to create a complex, beautiful, and adaptive structure. The randomness is not outside the design, it is the medium through which the design expresses itself in a non-deterministic world. Could the universe be similar? Perhaps the laws of physics are the cosmic DNA, the underlying set of rules and constants that define the potentialities. The quantum fluctuations are then the necessary randomness that allows for the rich, complex, and unpredictable tapestry of the cosmos to unfold. Without that randomness, the universe might be perfectly uniform, perfectly homogeneous, and perfectly sterile. A designed universe that is completely deterministic would be a static, boring, and lifeless clockwork. A universe that incorporates genuine randomness at its foundation is one capable of surprise, creativity, and the emergence of genuine novelty. In this view, the question is not randomness or design, but rather, could randomness be the tool of design? The quantum fluctuations that gave us our universe may not be evidence of a universe without a creator, but rather of a creator who valued freedom, complexity, and the potential for spontaneous beauty over rigid, predictable control. This doesn't prove intent, but it opens a door, suggesting that the presence of chance at the foundation of everything does not automatically slam that door shut. It leaves us with a universe that is neither a sterile machine nor a meaningless accident, but something far more mysterious and wondrous, a cosmos where the seeds of galaxies were sown by quantum chance, and where the potential for life was written into the laws of physics, but its actual realization was left to the creative, unpredictable play of randomness. While dark energy acts as the mysterious accelerator pushing the universe apart, and baryonic matter forms the glittering cities of the cosmic web, there is a silent, unseen architect whose gravitational hand sculpts the entire structure and dictates the local pace of expansion: dark matter. This enigmatic substance, which makes up about 85% of all matter in the cosmos, doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet its influence is absolutely everywhere, a gravitational force so dominant that it dictates where galaxies can form and how fast the space around them can stretch. Think of dark matter not as a driving force for expansion, but as the ultimate cosmic zoning board, creating the dense urban centers and the empty deserts that dark energy then acts upon in dramatically different ways. The most powerful evidence for this invisible scaffolding comes from watching how galaxies themselves behave. In the 1930s, astronomer Fritz Zwicky noticed something bizarre about the Coma cluster of galaxies. The individual galaxies were moving so fast that the gravitational pull from all the visible stars and gas should not have been nearly strong enough to hold the cluster together. It should have flown apart. The only explanation was that there was a huge amount of unseen matter, its gravity providing the extra glue. Decades later, Vera Rubin provided even more compelling proof by studying the rotation of individual spiral galaxies. She found that stars at the outer edges of galaxies orbit just as fast as those near the center, which defied the laws of gravity as we knew them. If a galaxy were made only of the stars we can see, those outer stars should be moving much more slowly, like planets farther from the sun. The fact that they weren't meant each galaxy was embedded within a vast, massive sphere of this invisible material, a dark matter halo, whose gravity was governing the motions of everything within it. We can now map the distribution of this dark matter across the universe using a phenomenon predicted by Einstein's general relativity: gravitational lensing. The immense gravity of a massive object like a galaxy cluster warps the very fabric of spacetime around it, acting like a lens that bends and distorts the light from more distant galaxies behind it. By carefully analyzing these distorted, stretched, and magnified images of background galaxies, astronomers can create a detailed map of the mass in the foreground cluster. Time and again, these maps reveal that the bulk of the mass, the source of this incredible gravitational power, is not where the visible galaxies are. It forms a much larger, smoother, and more massive halo that envelops the entire cluster. This technique has allowed us to chart the entire cosmic web of dark matter, revealing the same filaments and voids we see in the visible universe, but built from this mysterious, invisible substance. This uneven distribution of dark matter is the primary reason the expansion of the universe isn't uniform. imagine the cosmos as a vast, elastic sheet. Now place heavy weights on this sheet to represent the immense concentrations of dark matter in galaxy clusters and filaments. The sheet will dip and curve deeply around these weights. In these regions of strong curvature, these gravitational wells, the expansion of the sheet itself is strongly resisted. The powerful inward pull of gravity fights against the outward push of dark energy, creating a local environment where the expansion is significantly slowed. Our own Milky Way galaxy, for instance, is not expanding because the gravitational bond forged by its dark matter halo is far too strong for dark energy to overcome on these local scales. Now travel out into the immense cosmic voids, the empty spaces between these dark matter filaments. Here, the sheet is almost flat. There are no heavy weights, very little matter of any kind, and therefore an extremely weak gravitational pull. In these regions, dark energy meets almost no resistance. With nothing to hold it back, it can push the fabric of space apart at a much faster rate than the cosmic average. The void doesn't just expand, it accelerates. This creates a fascinating dynamic where the rate of expansion at any given point in the universe is not a single number from a textbook, but a local value determined by the tug of war between the outward push of dark energy and the inward pull of gravity, which is itself dictated by the local density of dark matter. The universe isn't expanding in one way, it's expanding in millions of different ways simultaneously, a symphony of rates conducted by the invisible hand of dark matter's distribution. This reveals the beautiful, complex interconnectedness of the cosmos. Dark matter shapes the structures. Baryonic matter, the ordinary atoms we're made of, follows the gravitational blueprint laid down by dark matter, falling into its potential wells to form the stars and galaxies we see. And dark energy then acts upon this pre-existing structure, expanding the empty voids rapidly while making far less headway against the dense knots held fast by dark matter's grip. It's a cosmic dance between three partners, each with a radically different role, and their combined interaction is what creates the non-uniform, anisotropic expansion we are now struggling to measure and understand. The story of the universe's expansion cannot be told by dark energy alone. It is a tale written in the invisible ink of dark matter's gravitational signature. But for all the gravitational might of dark matter and the pervasive push of dark energy, there is a third player in this cosmic drama, one made of the stuff we can actually see and are intimately familiar with: baryonic matter. This is the ordinary matter, the atoms of hydrogen, helium, and everything else on the periodic table that constitute every star, every planet, and every one of us. While it makes up less than 5% of the universe's total mass energy content, its role is far from passive. Baryonic matter is the active, dynamic ingredient that takes the gravitational blueprint laid down by dark matter and builds upon it, adding intricate details and local complexities that further influence how space expands in its immediate vicinity. The story begins with the profound tendency of this ordinary matter to clump together. Under the relentless pull of gravity, vast clouds of primordial gas, already nestled within the immense halos of dark matter, begin to collapse. As these clouds contract, they fragment, and within these densest pockets, the pressure and temperature soar to the millions of degrees required to ignite nuclear fusion. A star is born. This process of star formation is the universe's primary mechanism for building up dense, massive structures. But stars are not just endpoints, they are powerful engines that, in turn, reshape their surroundings. The most massive stars live fast and die young, exploding as spectacular supernovae. These violent deaths blast vast quantities of newly forged heavy elements, the carbon, oxygen, iron essential for planets and life, back out into space, but they also do something else. They inject enormous energy into the surrounding gas. This phenomenon, known as feedback, is a crucial form of cosmic redistribution. Imagine a bustling construction site where the very act of building a skyscraper also involves periodically setting off controlled explosions that clear the area and push building materials out to the suburbs. That's what supernova feedback does. This outpouring of energy can heat up nearby gas clouds, preventing them from cooling and collapsing to form new stars too quickly. In some cases, it can even push gas completely out of a small galaxy's gravitational grasp, effectively halting its growth. This process doesn't just create dense regions, it actively regulates their density and distribution, preventing matter from piling up in one spot and instead creating a more complex, hierarchical structure of stars, star clusters, and galaxies of various sizes. We can see this play out vividly in our own cosmic backyard, the local group, dominated by our Milky Way and the Great Andromeda Galaxy. Both are massive spiral galaxies, each containing hundreds of billions of stars. Their immense gravitational pull doesn't just hold themselves together, it governs an entire entourage of smaller satellite galaxies, like the Large and Small Magellanic Clouds. The gravitational interplay within this group creates a local environment where the expansion of the universe is completely overpowered. The space between the Milky Way and Andromeda isn't expanding at all. In fact, these two giants are caught in a mutual gravitational dance, hurtling towards each other at about 110 kilometers per second, destined to collide and merge billions of years from now. On these local scales within galaxy groups and clusters, the gravitational bonds forged by baryonic and dark matter are so strong that they create islands of stability, cosmic archipelagos where the general expansion of the universe is effectively paused. This introduces a critical nuance to our understanding of expansion. The universe is expanding, but individual galaxies, stars, and planets are not. The atoms in your body are not being pulled apart because the electromagnetic and gravitational forces holding you together are vastly stronger than the subtle tug of dark energy on your personal scale. Expansion only wins in the vast, empty deserts between these gravitational islands. So when we talk about the expansion rate being non-uniform, we're often talking about the difference between the frantic stretching of a million light-year wide void and the utterly still, self-gravitating space within a galaxy cluster like Virgo or Coma. The visible matter, the baryonic stuff, is what defines the shorelines of these islands, making the uneven expansion not just a theoretical concept but a palpable reality we can point to in the night sky. It grounds the most abstract cosmological ideas in the familiar pinpricks of light we see overhead, reminding us that we are living in one of those dense, slow-moving regions, watching the rest of the cosmos stretch away into the distance. To truly grasp the uneven expansion of the cosmos, we must journey into its emptiest, most desolate neighborhoods, the cosmic voids. These are not just gaps between galaxies. They are staggering abysses of nothingness, vast regions of space that can span hundreds of millions of light years and contain almost no galaxies, stars, or detectable matter. If the universe's dense galaxy clusters are its glittering, bustling metropolises, then the voids are its immense, dark, and accelerating deserts. And it is in these profound emptinesses that the mysterious push of dark energy operates with its most dramatic and unbridled force, creating the most extreme examples of non-uniform expansion we can observe. Consider the Boötes Void, one of the largest and most famous of these cosmic deserts. Discovered in the 1980s, this spherical region of space is roughly 700 million light-years across. To put that incomprehensible scale into perspective, if our Milky Way galaxy were the size of a grain of sand, the Boötes void would be a cavernous emptiness nearly the size of a professional sports stadium. Initially, astronomers found only a handful of galaxies in this entire colossal volume, a number so low it defied all expectations of the average distribution of matter. While later, more sensitive surveys have found a few more, the void remains overwhelmingly, profoundly empty. This is not a place you would want to be. The distance between any 2 points is so immense, and the light from any source so faint, that the inside of a void would appear as a perfect, unbroken blackness to the human eye, with the nearest galaxy so far away it might not even be visible as more than a faint smudge. This incredible lack of matter is the key to understanding why voids are the universe's acceleration zones. Remember the fundamental cosmic tug of war. Gravity pulls inward, dark energy pushes outward. In a galaxy cluster, the immense gravitational pull from all the visible stars, and more importantly, the enormous halo of dark matter, acts as a powerful brake on expansion. But in a void, there is almost nothing to pull back. The gravitational resistance is vanishingly small. This allows the repulsive effect of dark energy to operate almost unimpeded. Consequently, the space within a void doesn't just expand at the average Hubble rate, it expands faster. The fabric of spacetime itself is stretching more rapidly there than in the denser regions surrounding it. It's like being in a region where the very rubber of the balloon is thinner and more elastic, stretching with greater ease. We don't have to just theorize about this, we can measure it directly. Astronomers use large redshift surveys, like the Sloan Digital Sky Survey, to map the universe in 3 dimensions. By precisely measuring the redshift of galaxies, how much their light is stretched by the expansion of space, scientists can calculate their velocity away from us. When they study galaxies that are embedded within or on the boundaries of these vast voids, they find something remarkable. These galaxies are receding from us faster than the standard Hubble flow would predict for their distance. This isn't because the galaxies themselves are moving through space at unusual speeds. It's because the space within the void itself is expanding at an accelerated rate, carrying the galaxies along with it like raisins in a piece of dough that is rising much faster than the rest of the loaf. This measurable velocity field provides direct observational proof that the expansion rate is not a single universal constant, but a variable that depends critically on your local environment. This behavior has profound implications for the entire cosmic web. Voids are not static bubbles, they evolve and grow over time. As the space inside a void expands faster than its surroundings, it effectively pushes against the walls of the surrounding filaments and clusters. This creates a fascinating dynamic where the voids are not passive empty spaces, but active players in shaping the large-scale structure of the universe. Their accelerated expansion stretches and pulls on the cosmic web, helping to define the boundaries of filaments and potentially influencing the flow of matter into the great galaxy clusters. The entire cosmos can be thought of as a network of these growing voids, each one jostling and pressing against its neighbors, with all the bright structures we see merely tracing the dense boundaries where these bubbles of emptiness meet. This dynamic view transforms our image of the cosmos from a static web to a living, breathing, and stretching entity, with the voids acting as the driving engine of its ongoing evolution and its most striking anisotropy. The story of cosmic expansion is not a simple one-note song with a constant tempo. It's a symphony in multiple movements, each with its own rhythm and character, changing dramatically over the nearly 14 billion-year history of the universe. To understand why expansion isn't uniform today, we have to listen to this entire cosmic symphony, from its explosive opening notes to its current, accelerating crescendo. The rate at which space stretches has never been a fixed number on a dial. It is a value that has evolved, shifted, and been influenced by the changing balance of power between the fundamental constituents of the cosmos. In the very first fleeting moments during the inflationary epoch, the universe expanded at a rate that is literally unimaginable, doubling in size perhaps 100 times in a fraction of a second. This was expansion on steroids, driven by a unique form of energy that temporarily made the gravitational pull of all matter irrelevant. This period didn't just make the universe enormous, it also set the initial conditions. The quantum fluctuations that were magnified during this time created the minute density variations, the slightly overdense and underdense regions, that would become the template for all future structure. Crucially, during this ultra-smooth inflationary phase, the expansion was uniform. It stretched the universe into a state of incredible homogeneity and anisotropy, but it also imprinted the tiny seeds of future irregularity onto that smooth canvas. When inflation ended, that unique energy decayed, reheating the universe and filling it with the hot plasma of the Big Bang. The baton of expansion was passed to the momentum of the initial explosion and the gravitational influence of matter and radiation. For the next several billion years, gravity was the dominant conductor. The universe continued to expand, but the relentless gravitational pull of all the matter, both dark and visible, acted as a brake, steadily slowing the expansion down. Imagine a rocket launched from Earth. It keeps moving outward, but Earth's gravity constantly tugs on it, slowing its ascent. This was the universe during its matter-dominated era. In this period, the initial density variations planted by inflation began to grow. Gravity is an amplifier of contrast. It pulls more matter into the already slightly denser regions, making them even denser, while simultaneously draining matter away from the less dense regions, making them emptier. This gravitational collapse created the first galaxies and clusters in the densest knots, while the underdense regions began to evolve into the first proto-voids. Even though the overall expansion was slowing everywhere, it was already beginning to happen at slightly different rates, slower in the dense regions where gravity was strong, and a little faster in the emerging voids where gravity's grip was weaker. A pivotal turning point in this cosmic story occurred around 5 billion years ago. The universe had expanded and diluted so much that the particles of matter were spread incredibly far apart. Their collective gravitational pull, which weakens with distance, became too feeble to continue slowing the expansion effectively. It was at this point that a previously minor player stepped into the spotlight: dark energy. Because dark energy is a property of space itself, its density remains constant even as the universe grows. As the universe became larger and more empty, the energy density of matter plummeted, but the density of dark energy stayed the same. This meant that around 5 billion years ago, the repulsive push of dark energy finally overcame the attractive pull of matter, and the expansion of the universe began to accelerate. We now live in the dark energy-dominated era. This historical perspective is absolutely crucial for deciphering the anisotropies we see today. The non-uniform expansion isn't a static picture, it's a dynamic process that has been evolving for billions of years. The faster expansion in voids today is a direct consequence of their evolutionary history. They started as slightly underdense regions in the early universe. As gravity amplified structures elsewhere, it also amplified these emptinesses, evacuating them further. For eons, the expansion within them was only marginally faster. But once dark energy took over, these regions, with their incredibly weak gravitational fields, became the perfect environment for acceleration to run wild. Conversely, the dense clusters and filaments have been held together by their own immense gravity for so long that they have built up a powerful resistance. a gravitational inertia that continues to locally counteract the global acceleration. This is why understanding the full timeline is key. The expansion rate we measure in any given region isn't just about what's happening now. It's the culmination of its entire history, a history written by the initial conditions from inflation, shaped by the relentless pull of gravity during the matter-dominated era, and now being rewritten by the mysterious push of dark energy. The universe's expansion has moved through distinct phases: inflation, deceleration, and acceleration, and the fingerprints of each phase are still visible in the complex, uneven pattern of growth we observe today. The anisotropy is not a flaw. It is a living record, a cosmic history book telling the story of how the universe grew up and how the balance of power between its fundamental forces has shifted, creating the beautifully textured and dynamic cosmos we call home. But the persistent cracks appearing in our standard cosmic model, from the Hubble tension to the evidence for anisotropic expansion, have forced cosmologists to do what they do best: question their assumptions and dream up new possibilities. This has led to a fascinating frontier of theoretical physics, a vibrant exploration of alternative cosmological models that dare to challenge the reigning champion, Lambda CDM. For all its success, Lambda CDM makes a critical assumption that on the largest scales, the universe is homogeneous and isotropic, leading to a uniform expansion. What if that foundational assumption is the very thing holding us back? A new generation of theories is now asking if we've been oversimplifying the cosmos, proposing that its inherent lumpiness and irregularity might be the key to unlocking its deepest secrets. One particularly intriguing path questions not the distribution of matter, but the very nature of gravity itself. Lambda CDM is built upon Einstein's general relativity, which has passed every test thrown at it for a century. But what if relativity, as magnificent as it is, needs a tweak on the vastest scales? This is the premise of modified gravity theories, the most famous of which is MUND, or modified Newtonian dynamics. Originally proposed by Mordechai Milgrom to explain the rotation of galaxies without dark matter, MUND suggests that gravity behaves differently under conditions of extremely low acceleration. While MUND itself has struggled to explain all cosmological observations, it has inspired a broader class of relativistic modified gravity theories. These models attempt to adjust Einstein's equations to account for the accelerated expansion and large-scale structure without, or with less, dark energy and dark matter. The appeal is undeniable. It seeks to solve two mysteries, dark matter and dark energy, with a single elegant revision of our understanding of gravity. However, these models face an uphill battle, as they must perfectly replicate all the successful predictions of general relativity in our solar system while producing different effects on cosmic scales, a tightrope walk that has proven incredibly difficult to achieve. Another compelling line of attack fully embraces the universe's obvious lumpiness. These are the inhomogeneous models which discard the idealization of a perfectly smooth cosmos from the outset. A brilliant example is the Swiss cheese model developed by theorists like Thomas Buchert. Imagine the universe as a block of Swiss cheese. The dense, cheesy parts represent our galaxy clusters and filaments, where gravity is strong and expansion is slowed. The holes represent the vast cosmic voids, where the low density allows expansion to proceed much faster. In a uniform model, we average everything out into a smooth, creamy paste and get a single expansion rate. But a Swiss cheese model doesn't average the ingredients. It calculates the overall expansion by carefully accounting for the different rates in the holes and the cheese. The fascinating result is that the combined effect of these rapidly expanding voids can mimic the appearance of a cosmological constant, creating an overall accelerated expansion without needing a mysterious dark energy. In this view, the acceleration isn't driven by a new force. It's an illusion created by the fact that we are observing the cosmos from within a dense region, and the emptier voids are stretching space around us, pulling the universe apart. It's a radical shift in perspective. The problem isn't that we need new physics, but that we've been misapplying the old physics by oversimplifying the geometry of the cosmos. Other theorists are sticking closer to the lambda-CDM framework, but are making its key component more dynamic. Instead of a static cosmological constant, they propose models of dynamic dark energy, often called quintessence. Think of this as a new, evolving field that permeates space. Unlike the stubbornly constant energy of lambda, a quintessence field can change in density and even in its repulsive strength over time and, crucially, across space. This could naturally lead to variations in the expansion rate. If this energy field clumps slightly, attracted to or repelled by matter, it could be stronger in voids and weaker in clusters, directly accounting for the anisotropic expansion patterns we're beginning to detect. This wouldn't remove the mystery of dark energy, but it would make it a more complex and interesting character in the cosmic story, one with a personality that changes over billions of years and across billions of light years. Researchers like Paolo Salucci have contributed to this rich tapestry of ideas by meticulously mapping the distribution of dark matter within galaxies and finding consistencies that sometimes challenge the simplest predictions of the Standard Model, further fueling the debate. The beauty of this moment in cosmology is not that any one of these alternatives has proven itself superior, but that the community is actively exploring such a diverse and creative toolbox of explanations. It demonstrates a fundamental strength of science, its relentless self-questioning. The goal isn't to defend a single theory to the death, but to follow the data wherever it leads, even if that path forces us to reconsider the most fundamental pillars of our understanding. These alternative models, from modified gravity to Swiss cheese cosmologies, are not just wild speculations, they are necessary stress tests for our prevailing theories. They force us to ask if the assumption of uniformity, which has served us so well for so long, might ultimately be an oversimplification of a far more textured, complex, and interesting reality. So how do we actually know that the expansion rate might be different in one part of the sky compared to another? How do we transform a grand theoretical idea into a hard, measurable fact? The answer lies in the incredible toolbox of observational astronomy, a collection of techniques and technologies so precise they can measure the subtle stretching of space itself across billions of light years. This isn't about guessing. It's about a meticulous, multi-pronged forensic investigation of the cosmos, where every method provides a different piece of the puzzle, and where the greatest challenge is often overcoming the limitations of our own magnificent instruments. The most fundamental tool in this investigation is the measurement of redshift. When a galaxy moves away from us, the wavelength of its light is stretched, shifting it toward the red end of the spectrum. This is the cosmic Doppler effect, and it's our primary indicator of recessional velocity. But to turn that velocity into a precise expansion rate, we need to know something even more crucial: the galaxy's true distance. This is the heart of the challenge. Measuring distance in the universe is incredibly difficult, and astronomers have developed a clever ladder of techniques, each one calibrating the next to reach across the vast cosmic depths. The first rung on this cosmic distance ladder uses a method called parallax, the same technique your brain uses to perceive depth with two eyes. By observing a star from opposite sides of Earth's orbit around the Sun, we can measure its tiny apparent shift against the background of more distant stars and calculate its distance through simple trigonometry. This works for the very closest stars, providing a solid foundation. The next rung relies on a special class of stars called Cepheids variables. These stars pulsate with a regular rhythm, and crucially, the period of their pulsation is directly related to their true intrinsic brightness. By measuring the period of a Cepheid's pulse, we know how bright it should be. By then measuring how dim it appears to be from Earth, we can calculate its distance with remarkable accuracy. This is where the Hubble Space Telescope earned its stripes, peering into nearby galaxies to find and study these cosmic lighthouses, painstakingly calibrating the first steps of the ladder. For even greater distances beyond the clear resolution of Cepheid variables, astronomers need a brighter standard candle. This is where Type Ia supernova come in. These spectacular stellar explosions occur when a white dwarf star accretes enough mass from a companion to trigger a runaway thermonuclear explosion. Because this critical mass is always the same, the peak brightness of these supernovae is incredibly consistent. When one goes off in a distant galaxy, it can outshine the entire galaxy itself, making it visible across billions of light years. By measuring its peak brightness, astronomers can determine its distance with high precision. It was precisely this method that two independent teams used in the late 90s to make the shocking discovery that the universe's expansion is accelerating, a finding that won them the Nobel Prize and introduced us to the mystery of dark energy. But the toolbox doesn't end there. Another powerful and completely independent method uses not stars, but the very fabric of the universe's large-scale structure. This technique focuses on baryon acoustic oscillations. In the early universe, pressure waves, effectively sound waves, rippled through the hot plasma. When the universe cooled enough for atoms to form, these waves froze in place, imprinting a preferred scale on the distribution of matter. This scale, about 500 million light-years across, acts as a permanent cosmic ruler etched into the sky. By using enormous galaxy surveys like the Sloan Digital Sky Survey to map the positions of millions of galaxies, scientists can measure this standard ruler at different epochs of the universe's history. Seeing how the apparent size of this ruler changes with redshift allows them to measure the expansion rate over time, providing a crucial check on the supernova results. The newest tool in the box is gravitational wave astronomy. When two massive objects like neutron stars merge, they send ripples through space-time itself. These gravitational waves carry information about the masses of the objects and the energy of the event. By detecting the waves, we can calculate the event's intrinsic strength, known as its amplitude. If we can also find the flash of light or electromagnetic counterpart from the same event with telescopes, we can measure its redshift. This combination gives us a direct, calibration-free measurement of distance, a whole new way to climb the cosmic ladder that is independent of all the other rungs. Each of these techniques relies on breathtaking technology. Spectrographs break starlight into rainbows of color to measure minute redshift shifts. Space telescopes like Hubble and JWST peer above Earth's blurring atmosphere to see fainter, more distant objects with crystal clarity. Gigantic digital cameras on telescopes like the Vera C. Rubin Observatory will map billions of galaxies in unprecedented detail, and interferometers like LIGO and Virgo detect space-time ripples so small they are a fraction of the width of a proton. Yet for all their power, these measurements are fraught with challenges. Calibration is a constant battle. A tiny error in the measured brightness of a single Cepheid variable can propagate up the entire distance ladder, skewing the results. There's also cosmic variance, the fact that we can only observe one universe from one vantage point. Perhaps our local region is simply atypical, and our measurements aren't representative of the cosmic average. This is the constant, careful work of science, building multiple independent lines of evidence, checking and cross-checking for consistency, and relentlessly hunting down every possible source of error. It's a slow, meticulous process, but it's how we move from speculation to certainty, and how we are now gathering the first compelling evidence that the universe's expansion is not the smooth, uniform process we once imagined it to be. For centuries, humanity has gazed at the night sky and sought to find our place within it, often concluding that the cosmos was an orderly, designed, and purposeful creation. The medieval worldview, heavily influenced by thinkers like Thomas Aquinas, saw the universe as a perfect, nested set of celestial spheres, a divine clockwork operating with flawless, uniform precision. This was a cosmos that reflected a grand architect, a place where everything had its designated spot and moved according to a harmonious, predetermined plan. Our modern discovery that the universe is not only expanding but doing so unevenly, with chaotic voids and accelerating filaments, delivers a profound shock to this inherited sense of cosmic order. It doesn't just change our equations, it challenges the very stories we tell ourselves about reality and our role within it. This shift from a universe of perfect order to one of beautiful, underlying irregularity forces a philosophical reckoning. The great Enlightenment philosopher Immanuel Kant famously stated that two things filled his mind with ever-increasing wonder and awe: the starry heavens above and the moral law within. For Kant, the cosmos was a sublime manifestation of reason. But what happens to that sense of sublime wonder when we learn the starry heavens are not a fixed, eternal tapestry, but a dynamic and fundamentally uneven process? Does this irregularity make the universe more fascinating, more full of creative potential, or does it make it a more frightening, alien, and indifferent place? There's no single answer, but the question itself is deeply human. We are pattern-seeking creatures, and finding that the grandest pattern of all is imperfectly woven is existentially disruptive. Some might see in this cosmic anisotropy a refutation of any notion of design, a final step in the process that began with Copernicus, removing us not just from the center of space, but from a universe that was ever centered on us in the first place. If the expansion is lumpy and lawless, perhaps it points to a reality without a creator, or at least without one that cares about the specific details. Yet others might find a different, perhaps even deeper, theological implication. A universe that is perfectly uniform and predictable could be seen as a mere machine, ticking away according to a simple, predetermined script. But a universe with texture, with variation, with local freedom in its very expansion rate, could be interpreted as something more nuanced, a creation that incorporates both law and creativity, a canvas that allows for spontaneity and surprise. In this view, the irregularities aren't a sign of absence, but of a more complex and interesting kind of presence. This conversation extends beyond theology into the raw questions of human meaning. The existentialist thinkers of the 20th century, from Jean-Paul Sartre to Albert Camus, grappled with a universe they believed was devoid of inherent meaning, arguing that we must create our own purpose courageously in the face of a silent, indifferent cosmos. Our modern cosmological discoveries provide a powerful new backdrop for this philosophical stance. A perfectly uniform, mechanical universe might have felt like it had a purpose, even if we couldn't see it. But a universe that is fundamentally patchy, unpredictable, and anisotropic feels much more like the indifferent universe the existentialists described. It doesn't operate according to a single, simple, overarching rule that we can easily discern. This can be seen as liberating. If there is no grand, uniform design, then the meaning of our lives isn't written in the stars waiting to be discovered. It is entirely our own to invent and build here on our fragile planet with profound responsibility. Ultimately, the cultural and philosophical weight of this discovery reminds us that science is not conducted in a vacuum. Every time we point a telescope at the sky, we are not just collecting data, we are gathering pieces of a story that will inevitably change how we see ourselves. The move from a geocentric cosmos to a uniform expanding one to an anisotropic and accelerating one is more than a technical adjustment. It is a fundamental evolution in the narrative of human existence. It asks us to let go of older, simpler comforts and embrace a more complex, challenging, and arguably more awe-inspiring reality. The universe is not a perfect clock, nor a smooth, inflating balloon. It is a vast, evolving, and uneven masterpiece, and our ability to even perceive its irregularities is a testament to our unique, curious, and meaning-seeking place within its magnificent, sprawling web. But the most thrilling part of this story is that we are not at the end. We are standing at the very beginning of a new golden age of discovery. The puzzles we've uncovered, the Hubble tension, the hints of anisotropic expansion, the nature of dark energy are not dead ends. They are the signposts pointing toward the next great revolution in our understanding, and a new generation of cosmic cartographers is already preparing to answer the call. These are not just new telescopes, they are time machines and dark energy detectors, instruments of such staggering precision that they will peer into the deepest mysteries of the cosmos and rewrite the textbooks of tomorrow. Leading this charge is the James Webb Space Telescope, already dazzling us with its breathtaking images. But beyond the stunning pictures of stellar nurseries and distant galaxies, JWST is a powerful cosmological tool. Its unparalleled infrared vision allows it to see the very first galaxies that formed after the Big Bang, and with a clarity Hubble could never achieve. By observing the most ancient supernova and the earliest cosmic structures, JWST is providing a critical, independent measurement of the expansion rate in the universe's youth. This data is essential for testing whether the Hubble tension is a result of measurement error, new physics, or a genuine variation in expansion history. It's like getting a high-definition calibration of the cosmic distance ladder's very first rung, allowing us to check our work with a precision we've never before possessed. While JWST looks deep into the past, the European Space Agency's Euclid mission is conducting a massive, wide-angle survey of the more recent universe. Launched in 2023, Euclid is designed to create the largest and most accurate 3D map of the cosmos ever made, charting billions of galaxies across 10 billion years of cosmic history. Its primary mission is to investigate the dark universe by measuring two key phenomena: weak gravitational lensing and baryon acoustic oscillations. By watching how the light from distant galaxies is warped by the invisible web of dark matter, Euclid will trace the distribution of this mysterious substance with unprecedented detail. And by mapping the BAO standard ruler across different epochs, it will measure the rate of the universe's expansion and the growth of its structures with phenomenal accuracy. Euclid's vast statistical power is what makes it so unique. It's not looking at one beautiful object at a time, but at the entire cosmic web, searching for the subtle imprints that dark energy and cosmic anisotropy have left on the grandest of scales. On the ground, the Vera C. Rubin Observatory in Chile is preparing to undertake a similar, but even more expansive endeavor. With its breathtakingly large mirror and a camera the size of a small car, Rubin will photograph the entire available sky every few nights for a decade. This legacy survey of space and time will not be a static picture. It will be a motion picture of the universe, detecting billions of galaxies and millions of transient events like supernova. This incredible torrent of data will allow scientists to track the expansion of the universe in real time and in every direction, creating a dynamic map of the Hubble flow that could finally reveal clear, unambiguous evidence for anisotropies. If one part of the sky is genuinely expanding faster than another, Rubin's relentless all-sky watch will be the instrument that finds it, and the toolbox doesn't stop there. The Nancy Grace Roman Space Telescope, set to launch later this decade, will join this effort with a wide field view that complements Hubble's sharpness. The Laser Interferometer Space Antenna, or LISA, will open an entirely new window on the cosmos by detecting low-frequency gravitational waves from the mergers of supermassive black holes, providing a completely independent way to measure cosmic distances and probe the very fabric of spacetime. Each of these missions approaches the mystery from a different angle, with a different technique, creating a powerful network of cross-checking evidence that will either confirm our standard model or finally break it open to reveal the new physics lying beneath. The potential discoveries are as thrilling as they are profound. These next-generation tools could resolve the Hubble tension once and for all, revealing whether it was a systematic error or a doorway to a deeper truth. They could finally tell us if dark energy is a simple cosmological constant or a dynamic field like Quintessence that changes over time and space. They could even uncover evidence that is completely unanticipated, perhaps a statistical signature in the distribution of galaxies that hints at a collision with another universe in the multiverse, or a strange repulsion in the voids that goes beyond anything Einstein conceived. This is not the end of the story, it is the end of the preface. We are living in the moment when the questions have been sharpened to a fine point, and the tools to answer them are finally coming online. The greatest chapters in our understanding of the cosmos are not behind us in the history books. They are waiting to be written in the light of the stars, collected by these magnificent machines and interpreted by the curious, relentless minds of the scientists who built them. The adventure is just beginning, yet for all its grandeur and abstract mystery, this cosmic puzzle of uneven expansion is not some distant intellectual game with no connection to our daily lives. It's easy to look at the vast scales involved and wonder, why does any of this matter to us? The answer is that this kind of fundamental, curiosity-driven research is one of humanity's most powerful engines for progress, touching our lives in ways both profound and practical. Pushing the boundaries of our understanding of the cosmos doesn't just satisfy a deep human yearning to know our place in the universe. It consistently leads to unexpected breakthroughs that ripple through our technology, our economy, and our global society. Consider the most ubiquitous example, the global positioning system in your smartphone. Every time you use it for directions, you are relying on Einstein's theory of general relativity. The satellites that beam those signals to your phone are moving fast enough and are far enough out of Earth's gravity, well, that time itself runs at a slightly different rate for them than it does for us on the surface. If the engineers who designed GPS had not accounted for these relativistic effects, the system's pinpoint accuracy would degrade by about 10 kilometers per day, rendering it useless in a matter of minutes. This isn't a minor correction. It is the very foundation of a technology that now guides everything from aviation and shipping to emergency services and everyday travel. General relativity was once the most abstract of ideas, a revolutionary new way to think about gravity, space, and time, with no conceivable practical application. Today, it is literally in your pocket, helping you find your way. The quest to understand dark energy and the uneven expansion of the universe is operating on this exact same frontier. The technologies we are developing to make these exquisitely precise measurements, faster computers, more sensitive sensors, advanced materials, and complex algorithms for processing unimaginable amounts of data, are already finding their way into other fields, from medical imaging to data science, pushing the boundaries of what is technically possible. Beyond the tangible technological spin-offs, this research represents a monumental investment in pure knowledge, and that investment has an inherent ethical value. In a world often focused on short-term gains and immediate utility, dedicating vast resources to questions that may not have a practical payoff for generations is a powerful statement about who we are as a species. It is an affirmation that understanding the universe for its own sake is a worthy human endeavor. This pursuit of knowledge is a global project that transcends national borders, political disagreements, and cultural differences. Massive international collaborations, like those behind the Euclid Space Telescope or the Vera-C Rubin Observatory, bring together thousands of scientists, engineers, and technicians from dozens of countries, all working toward a common goal of understanding. This kind of cooperation builds bridges, shares knowledge, and fosters a sense of shared human purpose on a planet that often feels deeply divided. It reminds us that we are all passengers on the same pale blue dot, looking out at the same magnificent cosmos and trying to make sense of it together. There is also a profound ethical dimension to simply choosing to look up and ask these big questions. It is an act of responsibility toward future generations. We are the beneficiaries of centuries of scientific inquiry undertaken by people who could not have possibly foreseen how their discoveries would one day transform the world. They planted trees whose shade they knew they would never sit under. By continuing to fund and support fundamental research into the deepest mysteries of the universe, we are planting those same trees for those who will come after us. We are ensuring that the great journey of discovery does not end with us, that the map of reality continues to be filled in, offering new insights, new technologies, and new perspectives we cannot yet imagine. The value isn't just in the answers we might find, but in the better, more curious, and more collaborative people we become in the process of searching for them. This cosmic curiosity is not a diversion from the pressing problems on Earth. It is part of the very same human spirit that strives to solve them, fueled by the same relentless drive to understand, to improve, and to explore. Now, one of the most common and understandable misconceptions about the expanding universe is the idea that everything is getting bigger. It's a natural assumption to make. If space itself is stretching, then shouldn't the space between the planets, the atoms in our bodies, and even the fabric of our measuring tapes be stretching too? The answer is a resounding no, and the reason is one of the most fundamental forces in the cosmos, gravity. While the expansion of space is a powerful effect on the very largest scales, it is incredibly weak on local scales. The gravitational bonds that hold objects together from solar systems and galaxies down to you and the chair you're sitting on are overwhelmingly stronger than the minuscule tug of the universe's expansion. Think of it like this: you can try to pull two powerful magnets apart, but their attraction to each other is far stronger than your pulling force. On a cosmic scale, dark energy is trying to pull the solar system apart, but the sun's gravitational grip on the Earth is about 30 orders of magnitude, that's a 1 with 30 zeros after it, stronger. That's not a contest, it's a complete and utter domination by gravity. So, while the space between galaxy clusters is growing, the space within a cluster, a galaxy, or a planet remains completely untouched and unchanging because gravity has already won that battle. This leads us directly to the classic and wonderfully useful analogy of the raisin bread dough. Imagine the universe as a lump of dough with raisins scattered throughout, representing galaxies. As the dough is left to rise, it expands uniformly. Every raisin moves away from every other raisin, and the farther apart two raisins are, the faster they appear to recede from each other because there's more expanding dough between them. This is a perfect model for understanding the Hubble expansion on large scales. However, the crucial point this analogy illustrates is that the raisins themselves do not expand. They stay the same size. They are bound structures held together by their own internal forces, in this case, the sticky integrity of the raisin, just as galaxies are held together by gravity. The dough is what's expanding, not the raisins. So, when we look out into the universe, we see other galactic raisins moving away from us, with the most distant ones receding the fastest. But our own galaxy, the Milky Way raisin, and all the stars and planets within it, remain their same size, happily bound together and completely oblivious to the grand expansion happening in the vast cosmic dough between them. Another pervasive myth is the search for a center. In our raisin bread analogy, it seems like there must be a center to the loaf, a point from which everything is expanding. This is a misunderstanding born from thinking of the Big Bang as an explosion in space, like a bomb going off in an empty room, with debris flying outward from a central point. But the Big Bang was not an explosion in space, it was an explosion of space itself. A better way to picture it is to imagine the entire universe is the surface of an inflating balloon. Draw dots all over the balloon's surface to represent galaxies. Now, as you inflate the balloon, every dot moves away from every other dot. Critically, there is no center on the surface of the balloon. Every dot, from its own perspective, sees all the other dots moving away from it. An ant living on any one of those dots would rightly conclude it was at the center of the expansion. This is exactly our situation. We are not at a privileged center of the universe. From any galaxy, the view would look the same. All other galaxies would appear to be receding. The expansion has no center because it is happening everywhere at once. The center of the balloon's volume is not part of the surface, just as a hypothetical center of the universe's expansion is not a location within our observable spacetime. Finally, it's important to address the ultimate fate of these bound structures. While gravity securely holds our local group of galaxies together today, the future tells a more complex story. Because the expansion is accelerating, driven by dark energy, its influence is not static, it's growing. Billions of years from now, the distance between our local group and other distant galaxy clusters will be so vast that the expansion of space between us will be occurring faster than the speed of light. Their light will never be able to reach us again, and those regions of the cosmos will fade from view forever, vanishing beyond an event horizon. Eventually, all that will be left in our observable universe will be our own gravitationally bound supercluster, an island of stars in an otherwise impenetrable and expanding darkness. This isn't because the expansion is breaking apart our local bonds, but because it is isolating our island from all others. So, while we are safe from being pulled apart, we are not immune to the profound loneliness that the accelerating universe may eventually impose, a future where the cosmic story continues to unfold, but with an audience that can only see its own isolated chapter. But the most exciting part of all this is that you don't need a multi-billion-dollar telescope to be a part of this grand exploration. The age of the armchair cosmologist is here, and there are incredible ways for anyone with a curious mind and an internet connection to contribute to real scientific discovery. One of the most rewarding paths is through citizen science projects, where researchers have made their vast datasets available to the public, inviting us all to help them sort through the cosmic haystack to find the needles. The most famous of these is undoubtedly Galaxy Zoo. For over 15 years, this project has enlisted millions of volunteers to do something that computers still struggle with: classifying the shapes of distant galaxies. When you log on, you're presented with a stunning image of a galaxy taken by the Sloan Digital Sky Survey or the Hubble Space Telescope. Your task is simple but profound. Is it a smooth, fuzzy, elliptical blob or a majestic spiral with distinct arms? Is it merging with another galaxy in a cosmic dance? Every classification helps astronomers understand how galaxies form and evolve, and the collective power of millions of human eyes has led to the discovery of entirely new classes of objects, like the now famous green pea galaxies. It's a powerful feeling knowing that while you're sipping your coffee at home, you could be the first person to ever lay eyes on a particular galactic structure, making a genuine contribution to our map of the universe. If you're more interested in feeling the expansion of the universe firsthand, there are incredible simulations and interactive tools that bring these abstract concepts to life. Apps like Universe Sandbox allow you to become the master of your own cosmos. You can simulate the gravitational dance of the solar system, watch galaxies collide in slow motion, or even try to add your own dark energy component to a virtual universe and hit fast forward to see what happens. It's a breathtaking way to develop an intuitive sense for the physics we've been discussing. You can literally grab our Milky Way and Andromeda galaxies with your cursor and push them together to trigger their future collision, or create a vast void and watch it expand faster than the regions around it. This kind of hands-on play is more than just a game. It's a form of experimentation, allowing you to test hypotheses and see the consequences of different cosmological models play out on your screen. It turns you from a passive learner into an active participant, demystifying the immense scales and forces that shape reality. And this conversation shouldn't end when the video does. The true magic of exploring these mysteries is sharing the wonder and the questions they spark. That's why your voice is such a crucial part of this journey. What part of this cosmic story resonated most with you? Was it the quantum fuzziness at the dawn of time, or the immense, accelerating voids? What burning question about the universe keeps you up at night? Let me know in the comments below. Your questions and insights don't just help build a community of fellow space enthusiasts, they directly shape the content we create next. Your curiosity is our roadmap, guiding us toward the topics that matter most to you. This is how we turn a monologue into a dialogue, transforming a channel from a source of information into a shared home for everyone fascinated by the profound and beautiful mysteries of the cosmos we call home. Now let's zoom in on a specific and particularly puzzling piece of this cosmic puzzle, a real-world anomaly that astronomers have been grappling with for years. It's called the Dipole Anisotropy, and it serves as a perfect case study for why the idea of uniform expansion is being so seriously challenged. Imagine you're listening to a steady, uniform tone, but as you turn your head, the pitch seems to shift slightly higher in one ear and lower in the other. That's essentially what we've detected in the oldest light in the universe, the cosmic microwave background. This primordial afterglow should be almost perfectly smooth, a uniform blanket of microwave radiation coming at us equally from all directions. But it's not. There's a distinct, measurable dipole pattern. The light appears very slightly warmer, which also means slightly blue-shifted in one direction of the sky, and very slightly cooler and red-shifted in the exact opposite direction. The most straightforward explanation for this is our own motion. This is the same Doppler effect you experience when a siren on a speeding car sounds higher-pitched as it approaches you and lower-pitched as it speeds away. If our entire solar system is moving rapidly through space relative to the rest frame of the cosmic microwave background, we would expect to see exactly this kind of dipole. And indeed, calculations show we are moving. Our local group of galaxies is being pulled toward the immense gravitational attractor known as the Great Attractor and the even larger Laniakea supercluster at a staggering 600 kilometers per second. This motion neatly accounts for a large portion of the dipole signal we observe. It's a reminder that we are not passive, stationary observers. We are on a cosmic journey, and that motion leaves an imprint on how we see the universe. However, the plot thickens considerably when we compare this CMB dipole to other, completely independent measures of our motion. When astronomers look at the distribution and apparent motion of hundreds of thousands of galaxies, or the flux of distant quasars and radio sources, they also detect a dipole in their distribution. The puzzling part is that the dipole measured from these local, modern sources seems to be aligned with the CMB dipole, but it's also significantly larger. The amplitude of the motion it suggests is about twice what we see from the CMB. This discrepancy is a major headache for cosmologists. If both dipoles were solely caused by our peculiar motion, they should agree perfectly. The fact that they don't opens up a far more radical possibility. Perhaps not all of this signal is due to our movement. Maybe a part of it is genuine, a real, intrinsic anisotropy in the expansion of the universe itself. This is where the debate gets incredibly heated and fascinating. Could it be that the universe is not only expanding at different rates in voids versus clusters, but that the expansion has a preferred direction on the largest scales? Some studies have suggested that the Hubble constant itself might be slightly different when measured in one hemisphere of the sky compared to the other. This isn't some wild, fringe idea. It's a hypothesis being tested with the most rigorous data available from missions like Planck. Proponents of this view argue that the simplest model, a perfectly uniform universe, might be an oversimplification, and that these dipolar hints are the first evidence of a more complex, textured cosmos. They suggest we might be living in a universe with a subtle gradient in the density of dark energy, or perhaps even a relic large-scale flow from the unevenness of the early universe that never completely smoothed out. On the other side of the debate, many scientists caution that we must exhaust every possible mundane explanation before leaping to such revolutionary conclusions. They point to potential systematic errors, subtle biases in how we count galaxies or measure their distances, or unknown astrophysical effects that could be mimicking a larger dipole. The history of cosmology is littered with anomalies that eventually evaporated under closer scrutiny with better data. The scientific process is rightly conservative, demanding extraordinary evidence for extraordinary claims. This tension between the two interpretations, a measurement error or a cosmic revolution, is science at its most vital. It's a microcosm of the larger struggle to understand non-uniform expansion, a concrete example that takes this grand, abstract concept and grounds it in a specific, data-driven mystery that astronomers are actively trying to solve right now. The dipole anisotropy is more than just a curious irregularity. It's a focal point for a much deeper question about the fundamental character of our universe, a question whose answer could force us to rewrite our most basic understanding of cosmic evolution. Yet to truly grasp how this uneven expansion could be woven into the fabric of reality, we must return to the very theory that first gave us the language to describe a dynamic cosmos, Einstein's general relativity. This isn't a historical footnote, it is the living, breathing foundation upon which all of modern cosmology is built. At its heart, general relativity is a theory of geometry. It tells us that gravity is not a mysterious force pulling objects together, but rather the curvature of space-time itself. Massive objects like stars and planets create dimples in this four-dimensional fabric, and other objects simply follow the straightest possible paths through this curved landscape, which to us appears as orbital motion. This elegant idea completely revolutionized our understanding of the universe, and it is the indispensable tool we use to describe its birth, evolution, and ultimate fate. When we apply the equations of general relativity to the universe as a whole, we make a critical simplifying assumption to make the math tractable. We assume the cosmos is homogeneous and isotropic. This is the cosmological principle, and it leads us directly to the Friedmann-Lemaitre-Albertson-Walker metric, the specific solution that describes a smoothly expanding or contracting universe. From this, we derive the famous Friedmann equations. These are the master equations of Big Bang cosmology, governing how the scale factor of the universe, essentially a measure of its size, changes over time. They tell us how the expansion rate is determined by the combined densities of matter, radiation, and now dark energy. For a century, this beautifully simple model, assuming perfect smoothness, has been our gold standard, our cosmic concordance model. It predicted the expanding universe, the cosmic microwave background, and the abundance of light elements. Its success is undeniable, but what if our starting assumption is just that, a simplifying assumption and not a fundamental law? The universe, as we've seen, is clearly not perfectly smooth. It is lumpy with vast voids and dense clusters. General relativity is a local theory. It describes how space-time curves in response to matter and energy in any given region. It does not inherently demand that the entire universe be uniform. So, what happens when we relax that assumption and allow for the possibility that the expansion could be different in different directions? This is where we enter the realm of anisotropic cosmological models, and the mathematics becomes far more complex, but also far more revealing. The most well-known of these alternative frameworks are the Baryonic cosmologies. These are specific solutions to Einstein's field equations that describe a universe that is homogeneous. It looks the same at every point, but not isotropic. It has a preferred direction. In a Baryonic universe, space could be expanding at one rate along the x-axis and a different rate along the y and z-axis. Imagine a universe that isn't stretching like a perfect sphere, but more like an ellipse, becoming more elongated in one direction than the others over time. While our observations strongly rule out a highly anisotropic universe on the largest scales, the fact that these are valid solutions within general relativity itself is profoundly important. It tells us that the uniformity of expansion is not a requirement of the theory. It is an additional constraint we placed upon it based on our observations. The door was always open for a more complex reality. We can visualize this with a simple thought experiment. Picture a perfectly flat, taut rubber sheet representing empty, flat spacetime. Now place a single, incredibly heavy bowling ball in the center. The sheet will deform into a deep, smooth, funnel-like curve. This is the isotropic curvature we're familiar with. But now, instead of one bowling ball, imagine laying down a long, heavy metal rod. The sheet will now bend in a very different way, creating a trough-like depression. The curvature is no longer the same in all directions. It has a clear orientation. Now, scale this idea up to the entire universe. If the distribution of matter and energy itself has a large-scale directional preference, perhaps an immense, unseen cosmic structure or a gradient in the dark energy field, then the expansion of the spacetime fabric it creates could very well exhibit a similar anisotropy. The Friedmann equations would be an approximation, an average of a more complex directional expansion described by a Baryonic-like model. This doesn't diminish Einstein's legacy, it deepens it. It shows that his theory is not a rigid, finished edifice but an incredibly flexible and robust language, capable of describing a much wider array of cosmic possibilities than we initially applied it to. The modern search for hints of anisotropic expansion isn't a rejection of general relativity. It is its fullest and most sophisticated application. We are now using this 100-year-old theory to ask questions its creator could never have imagined, probing the subtle textures of the cosmos to see if the reality is a simple, uniform expansion or a more complex, nuanced, and directional growth. The continuity of scientific inquiry is breathtaking. We are still working within the framework Einstein gave us, but we are now using it to explore the very boundaries of its own assumptions, pushing our understanding of the universe closer to its true and perhaps wonderfully uneven nature. But to truly bridge the gap between the random quantum seeds of the early universe and the vast cosmic anisotropies we see today, we must venture to the very frontier of theoretical physics, to a challenge that has eluded the greatest scientific minds for nearly a century: the problem of quantum gravity. Our two most successful theories, general relativity, which governs the cosmos on its largest scales, and quantum mechanics, which rules the subatomic world, are fundamentally incompatible. They speak different mathematical languages and break down under extreme conditions, like the center of a black hole or the very first moment of the Big Bang. Unifying them into a single, coherent theory is perhaps the holy grail of modern physics, and it is within this quest that we might find the most profound explanations for why the universe expands the way it does. The core of the conflict is one of perspective. General relativity paints a picture of a smooth, continuous, and flexible spacetime, a stage upon which the cosmic drama unfolds. Quantum mechanics, on the other hand, reveals a world that is inherently grainy, probabilistic, and discontinuous at the smallest scales. So, what does spacetime itself look like if you could zoom in to the smallest possible level, the so-called Planck scale? This is where our current theories fail, and where new ideas like string theory and loop quantum gravity offer breathtaking, albeit speculative, glimpses. They suggest that the smooth cosmic stage might be an illusion, and that the fundamental fabric of reality might be woven from something far stranger, a texture that could naturally lead to an uneven expansion. String theory, for instance, proposes that the fundamental constituents of reality are not point-like particles but tiny, vibrating loops of energy. These strings vibrate at different frequencies, and each frequency corresponds to a different fundamental particle, like an electron or a quark. But for the math of string theory to work, it requires something our everyday experience cannot fathom: extra dimensions of space. Beyond the three we know, string theory suggests there could be 6 or 7 additional spatial dimensions, all curled up into an unimaginably tiny, complex shape at every single point in space. The way these extra dimensions are folded and curled, a concept known as compactification, determines the laws of physics in our observable, three-dimensional world. As theorists like Juan Maldacena have explored, this could mean that the strength of dark energy, or even its uniformity, isn't a fundamental constant but is instead set by the specific geometry of these hidden dimensions. If that geometry isn't perfectly uniform across the entire universe, perhaps due to quantum fluctuations during inflation, then the effective strength of dark energy could vary from place to place, creating a natural mechanism for anisotropic expansion. Loop quantum gravity, championed by physicists like Carlo Rovelli, takes a different but equally mind-bending approach. It doesn't propose extra dimensions but instead suggests that space itself is not continuous. Imagine the fabric of spacetime not as a smooth sheet, but as a network of incredibly tiny, finite loops woven together, a kind of spin foam, space is quantized. It comes in discrete, indivisible units of volume. This has a radical implication. There is a limit to how much space can be curved or compressed. This could resolve the pesky singularities at the hearts of black holes and the Big Bang, replacing them with a quantum bounce. For our cosmic expansion, this granularity of space could introduce a subtle, inherent graininess. If this quantum foam has a structure that isn't perfectly isotropic at the Planck scale, those microscopic asymmetries could have been amplified during the universe's initial rapid expansion, imprinting a preferred direction or a pattern of variation on the cosmos that persists to this day. The universe's large-scale lumpiness might be a direct reflection of its fine-grained quantum structure. Then there are principles that seem to be pulled directly from science fiction, like the holographic principle. This idea, deeply connected to string theory and black hole physics, suggests that all the information contained within a volume of space can actually be encoded on its boundary surface, like a cosmic hologram. Our three-dimensional reality might be a projection from a two-dimensional surface at the edge of the universe. This isn't just a philosophical curiosity. It's a serious mathematical proposition that could simplify our description of the universe. If true, it might mean that the equations governing the expansion and evolution of our 3D world are actually written in a simpler 2D language. Anisotropies in our expanding universe could then be traced back to irregularities or patterns on this fundamental holographic surface, a concept that challenges our very notion of where and how physical laws are defined. These ideas are, for now, firmly in the realm of theoretical speculation. We lack the technology to probe the Planck scale directly or to test these predictions with observational data. Yet they represent the leading edge of human thought, the place where our logic and mathematics are pushing us to confront the true, bizarre nature of reality. They don't just offer potential solutions to the problem of quantum gravity, they provide a new conceptual toolkit for understanding the cosmos. A universe born from a quantum bounce, built from granular loops of space, or projected from a distant holographic boundary, is a universe where perfect uniformity would be the true surprise. These frameworks naturally accommodate texture, variation, and asymmetry, suggesting that the non-uniform expansion we are beginning to measure isn't a problem to be solved, but a fundamental feature to be understood. It is the signature of a cosmos that is quantum to its very core, a reminder that the largest structures we see are forever tied to the smallest vibrations of reality. While the basic idea of a single, rapid inflationary period has been incredibly successful, the frontier of this theory has expanded into a fascinating jungle of new ideas, each trying to explain the specific details of our universe's explosive birth with even greater precision. Think of the original inflationary model as a powerful, single-speed engine that launched the cosmos. Newer theories are like adding a sophisticated transmission, fuel injection, and a GPS system to that engine, allowing for a much more nuanced and controllable journey. Two of the most compelling upgrades are known as multi-field inflation and warm inflation, and both open the door to a universe that is inherently more varied and complex from its very first moments. Multi-field inflation suggests that the driving force behind the universe's rapid expansion wasn't a single, monolithic energy field, but a chorus of different fields all interacting with each other. Imagine trying to paint a picture using only one color. You could create a shape, but it would be monochrome and simple. Now, imagine having an entire palette of colors to blend on the canvas. A multi-field model is like that. Each field has its own properties. Some might be dominant for a brief instant, while others fade in and out of importance. This interplay can produce a far richer and more varied set of outcomes. it could naturally generate the kind of slight irregularities and potential anisotropies in the expansion that we are now searching for. Instead of a single quantum fluctuation pattern being stretched, you have several different patterns overlapping and interfering with each other, creating a more complex cosmic tapestry right from the start. This doesn't just explain why the universe isn't perfectly smooth. It provides a mechanism for why its imperfections might have a specific, textured character that a single field could never produce. Then there's the concept of warm inflation, which turns the traditional cold, empty model on its head. Standard inflation pictures a universe expanding in a supercooled, vacuum-like state, with the inflationary field dominating in near-total isolation. Warm inflation proposes a much more chaotic and crowded nursery. It suggests that during this rapid expansion, the universe was actually full of particles, and that these particles interacted significantly with the inflationary field itself. Think of it like the difference between a single ice skater gliding smoothly across a pristine, empty rink, and that same skater trying to perform their routine in the middle of a bustling crowd. The interactions with the crowd, the bumps and jostles, fundamentally change the performance. In warm inflation, the interactions between the field and the hot, dense plasma of particles could have dissipated the field's energy in different ways across different regions, potentially creating local variations in how long inflation lasted or how efficiently it transferred energy into matter. This could have left behind a cosmos with a built-in predisposition for uneven expansion, its initial conditions forged in the heat of interaction rather than in cold, lonely isolation. The beauty of modern cosmology is that these aren't just abstract thought experiments. They are models that make specific, testable predictions. Researchers are now running incredibly sophisticated computer simulations to see what kind of universe each model would produce. By creating millions of virtual universes in a supercomputer, each with slightly different inflationary rules, scientists can compare the statistical fingerprints they produce, the specific patterns of hot and cold spots in the cosmic microwave background, the distribution of galaxy clusters, the subtle hints of gravitational waves, against our actual, observed universe. It's a cosmic matching game on the grandest possible scale. The data pouring in from observatories like the Planck satellite acts as the ultimate referee in this game. Planck's exquisitely detailed map of the CMB is the closest thing we have to a baby picture of the universe, and it is covered in fingerprints from its birth. Every theoretical model leaves a distinct set of prints. The current data strongly supports the basic inflationary paradigm, but it also places tight constraints on the more exotic variants. For instance, the lack of a detected primordial gravitational wave signal a specific kind of polarization in the CMB called B modes has already ruled out some of the simplest and most powerful single-field models. This negative result isn't a failure. It's a powerful steering force pushing theorists toward more complex and nuanced ideas like multi-field or warm inflation, which can produce a universe like ours without requiring such a strong gravitational wave background. This field is alive and buzzing with activity. At major conferences like the American Astronomical Society meetings or the specialized Morion Cosmology Conference, one of the hottest topics is always the latest analysis of CMB data and what it says about these next-generation inflationary models. Papers are published monthly arguing for one subtle variation over another, each trying to account for every last nuance in the data. The ongoing mystery of the Hubble tension and the hints of anisotropies have only added fuel to this fire, making the question of inflation's precise mechanics more urgent than ever. We are no longer just asking if inflation happened. We are now deep in the weeds asking how it happened, trying to discern the exact mechanics of the universe's first and most dramatic growth spurt. This vibrant, sometimes contentious, debate is a sign of a healthy and thriving scientific field, one that is getting ever closer to a truly complete understanding of our cosmic origins, an understanding that may finally explain why the universe we see today is so beautifully, mysteriously uneven. Now, if the universe isn't expanding at a single, uniform rate, this forces us to confront a truly mind-bending possibility. Our universe might not have a single, universal age. We're used to the idea that the cosmos is about 13.8 billion years old, a number we state with such confidence that it feels like a fixed fact. But that age is calculated based on a critical assumption that the expansion has been smooth and even everywhere, allowing us to trace the cosmic film backwards to a single, definitive starting point. If the expansion has actually been faster in some regions and slower in others, then that rewind button would work at different speeds in different places. The consequence is staggering. Some parts of the universe could be chronologically older than others. Think of it this way. Imagine two runners starting at the same line for a marathon, but one is on a smooth, level track while the other is on a track that's slightly downhill. They both start at the same moment, but the runner on the downhill track will cover more distance in the same amount of time. If you only knew the distance each had run and assumed they'd been moving at the same average speed, you'd mistakenly calculate that the downhill runner had been running for a longer period. Now apply this to cosmology, a vast cosmic void where expansion has been proceeding faster due to weaker gravity, is like the downhill runner. The space within it has stretched more over the same 13.8 billion years than the space within a dense galaxy cluster. If we were to use the current local expansion rate measured in that void to calculate its age, we might get a younger age because the faster expansion means it would take less time to reach its current scale. Conversely, in a dense cluster where gravity has been fiercely resisting the expansion, the slower local rate might suggest an older age for that region. This isn't just a mathematical curiosity, it's a direct challenge to our notion of a single cosmic clock ticking for everyone. This idea provides a fascinating new angle on one of cosmology's biggest headaches, the Hubble tension. The discrepancy between the early universe and late universe measurements of the expansion rate directly affects the inferred age of the cosmos. The early universe measurement from the Planck satellite, which assumes a smooth expansion history, gives us that 13.8 billion year figure. But the local measurement from supernova, which finds a faster expansion rate, would actually suggest a younger universe if taken at face value, perhaps only 12 or 13 billion years old. This age conflict is deeply troubling because it creates direct contradictions with other independent age dating methods. For instance, we can date the oldest stars in our galaxy by studying their composition and position on what's called the main sequence. Some of these ancient stars are robustly calculated to be over 13.5 billion years old. If the universe were only 12 billion years old, that would be impossible. You can't have stars that are older than the universe itself. But if expansion is anisotropic, this age paradox might simply vanish. We wouldn't be living in a 12 billion year old universe or a 13.8 billion year old universe. We would be living in a region of the universe where the local expansion history has been slower, making our local neighborhood older than the cosmic average. The ancient stars in our galaxy wouldn't be older than the universe. They would simply be a feature of our particular, slower expanding, and therefore chronologically older galactic neighborhood. The faster expansion rate we're measuring locally with supernova wouldn't be the global rate. It would be our current, amped-up local value, but when integrated over time, our region's past expansion was slower, allowing more time for those ancient stars to form. This reframes the Hubble tension not as an error in our stopwatch, but as a confusion over which of many cosmic clocks we should be reading. It suggests that the universe isn't a single entity with one birth certificate, but a vast and varied collection of regions, each with its own effective age, its own personal timeline within the grand cosmic story. This adds a profound temporal dimension to the spatial anisotropies we've been exploring, weaving time and space together into a single, complex, and non-uniform tapestry. If this journey through the uneven expansion of the universe has sparked a deeper curiosity in you, the good news is that this is just the beginning. The adventure of cosmic discovery doesn't have to end when this video does. There is a universe of incredible resources waiting for you to explore, designed for every level of interest, from the casually curious to the aspiring cosmologist. Let me point you toward some of the very best gateways to continue your exploration. For those who truly want to dive deep into the concepts, we've been discussing the nature of space-time, quantum mechanics, and the multiverse. There is no better starting point than Brian Greene's masterpiece, The Fabric of the Cosmos. This book is a marvel of scientific communication. Greene has a rare gift for translating the most complex ideas in theoretical physics into vivid, relatable metaphors without sacrificing their profound meaning. He will take you on a tour from Newton's absolute space and time all the way to the cutting-edge ideas of string theory and the holographic universe, making you feel like you have a front-row seat to the greatest intellectual show on Earth. It's the perfect next step to solidify your understanding and see how all these cosmic puzzles fit together into a grand, if still incomplete, picture. But books are just one way to learn. We are living in a golden age of scientific documentaries that bring the cosmos to life with stunning visuals and clear explanations. The classic PBS Nova series has countless episodes dedicated to cosmology, but for a truly transformative experience, seek out the miniseries adaptation of The Fabric of the Cosmos itself, hosted by Brian Greene. It visualizes concepts like inflationary expansion and higher dimensions in ways that are simply breathtaking. Another must-watch is the renowned Cosmos series. While both Carl Sagan's original Cosmos, A Personal Voyage, and Neil deGrasse Tyson's updated Cosmos, A Space-Time Odyssey are phenomenal, the sequel, Cosmos: Possible Worlds, delves even more directly into the multiverse and the future of humanity among the stars. These shows don't just inform you, they inspire a sense of awe and wonder that stays with you long after the credits roll. Of course, you don't need to spend a dime to access a treasure trove of cosmic knowledge. Some of the best resources are completely free online, thanks largely to the tireless work of public outreach by the world's leading space agencies. NASA website is an absolute wonderland for space enthusiasts. Their Universe section is constantly updated with the latest discoveries from the James Webb and Hubble telescopes, featuring jaw-dropping images and articles written to be accessible to everyone. For a more structured learning experience, the European Space Agency's website for the Euclid mission is a fantastic deep dive into the science of dark energy and dark matter, packed with animations, infographics, and easy-to-digest explainers that put you right on the cutting edge of the research we discussed. To truly feel like a part of the scientific process, I highly encourage you to follow the scientists and communicators who are sharing this journey in real time. Astrophysicists like Dr. Becky Smethurst, Dr. Sabine Hossenfelder, and PBS Spacetime have fantastic YouTube channels where they break down new papers, explain cosmic anomalies, and answer viewer questions with clarity and enthusiasm. They are your direct line to the latest developments and the passionate debates shaping our understanding of the cosmos. I will leave links to all of these resources, the books, the documentaries, the websites, and the channels, waiting for you in the description below. Think of them as your personal launch pad. Your curiosity is the most powerful tool you have, and with these resources, you have everything you need to fuel it, to ask bigger questions, and to keep looking up at the night sky with a deeper understanding of the magnificent, expanding, and beautifully uneven universe we call home. Of course, the most compelling insights don't come from a script, but from the scientists themselves, the men and women on the front lines of this cosmic investigation. Imagine for a moment that we could cut away to a clip of an interview with a leading cosmologist, someone like Dr. Wendy Friedman from the University of Chicago, who has spent decades refining our measurement of the Hubble constant. She leans forward, her expression a mixture of intense focus and genuine wonder, and says, "You know, when we first started this work, we were all expecting to measure a single number, a universal constant. The fact that we're now seriously debating whether that constant might actually be a variable, that it might depend on where you look, is both terrifying and exhilarating. It means we're on the verge of something new." Hearing it directly from her, seeing the passion in her eyes, transforms the Hubble tension from an abstract puzzle into a very human story of discovery and perseverance. Then picture a conversation with a theorist like Dr. George Efstathiou from the University of Cambridge, a key figure behind the Planck satellite's analysis of the cosmic microwave background. His perspective would ground the discussion in the sheer weight of the data. He might explain with a calm, measured authority, the standard model is beautifully self-consistent. But when the universe itself gives you a persistent discrepancy, a stubborn signal that won't go away no matter how many times you check your work, you have to listen. You have to at least entertain the possibility that the model, for all its success, is incomplete. His cautious, data-driven skepticism would provide the perfect counterbalance to the more speculative ideas, reminding us that extraordinary claims require extraordinary evidence, and that the scientific process is a marathon, not a sprint. To understand the more radical alternatives, we could hear from a proponent of inhomogeneous models like Dr. Thomas Buchert. His enthusiasm would be palpable as he describes the Swiss cheese universe. "We've been averaging out the cosmos for a century because the math was simpler," he might argue, but the universe isn't a smooth paste, it's full of holes. And when you actually do the math properly, accounting for these vast, expanding voids, you find that they can mimic the effects of dark energy all on their own. We might not need a mysterious new force, we might just need to do our accounting more carefully. This kind of first-hand explanation makes a complex theoretical model feel intuitive and compelling, connecting the abstract mathematics directly to the observable structures in the sky. These hypothetical interviews do more than just provide sound bites. They add a crucial layer of authenticity and dynamism. They show the scientific process in action, not as a dry collection of facts, but as a living, breathing, and often contentious conversation between brilliant, dedicated people. We see the personality behind the papers, the cautious optimists, the bold revolutionaries, the meticulous data analysts, all united by a shared sense of awe for the mystery they are trying to solve. Their personal insights bridge the gap between the impossibly vast scales of cosmology and our very human desire to understand, making the entire journey feel less like a lecture and more like we're peering over their shoulders, sharing in the moment of discovery as it unfolds. But how do we move from these raw numbers on a graph, these abstract equations, to a true understanding of what this uneven expansion actually looks like across the cosmos? This is where the power of modern computing transforms data into dazzling visual revelation. We are no longer limited to our telescopes. We can now build entire virtual universes inside supercomputers, running the laws of physics forward in time to see the cosmic story unfold before our eyes. These aren't just animations, they are rigorous scientific instruments, digital laboratories where we can test our theories and visualize the invisible forces shaping reality. The most sophisticated of these tools have names that sound like they're from science fiction, but their power is very real. Software like Gadget and Illustris TNG are the engines behind these cosmic simulations. Gadget, which stands for Galaxy and Assembly Generation under extreme thermodynamics, is a workhorse code used by cosmologists worldwide. It doesn't just track dark matter, it models the complex interplay of gravity, gas hydrodynamics, star formation, and the explosive feedback from supernova and black holes. It takes the initial conditions we see in the cosmic microwave background and then lets the clock run, simulating billions of years of evolution in a matter of weeks. Its more advanced successor, Illustris TNG, pushes this even further, creating some of the most detailed and breathtaking virtual universes ever produced. Imagine watching one of these simulations play out on a screen. It doesn't start with galaxies, but with a nearly smooth digital ocean of dark matter and gas. As the simulation begins, gravity starts its work. You can see it happen tiny. Random overdensities begin to pull in more material, growing from faint ripples into delicate webs of matter. These filaments, glowing with the simulated light of forming stars, stretch across millions of light years, connecting at dense, brilliant nodes that will become galaxy clusters. And between them, vast spherical voids begin to form and expand, growing emptier and darker as the eons tick by. The simulation doesn't assume uniform expansion. It calculates the gravitational pull and the push of dark energy at every single point. You can literally see the voids stretching faster, their boundaries becoming sharper, while the dense clusters struggle against the tide, expanding much more slowly. It's a cosmic dance of creation and emptiness, playing out in accelerated time, providing a visual proof that the universe's growth is inherently and beautifully uneven. The visuals these tools produce are more than just pretty pictures. They are a critical bridge between theory and observation. When a simulation like Illustris TNG generates a universe that looks statistically identical to the one we see through our telescopes with the right number of spiral galaxies, the right sizes of clusters, and the same vast network of voids, it gives us tremendous confidence that the physics coded into it is correct. But when we then tell that simulation to assume a perfectly uniform expansion rate, and it fails to reproduce the universe we see, the evidence becomes undeniable. The only way to get a virtual cosmos that matches our real one is to incorporate the varying strengths of gravity and dark energy to allow the voids to run wild and the clusters to hold their ground. These digital universes show us that anisotropy isn't a bug in the cosmos. It's a fundamental feature, and they allow us to see that feature in stunning, unforgettable detail, turning abstract equations into a grand, visual symphony of cosmic evolution. It's one of the great challenges of modern science communication. How do you share a genuinely thrilling and complex discovery without accidentally terrifying everyone or reducing it to a misleading soundbite? When it comes to the uneven expansion of the universe, the media often falls into this exact trap. You've likely seen the dramatic headlines, "Universe tearing apart at the seams," or "Cosmic crisis as expansion goes haywire." While these headlines are certainly attention-grabbing, they paint a picture that is more science fiction than science fact, and they often miss the profound nuance of what's actually happening. This sensationalism usually stems from a fundamental misunderstanding of scale. The anisotropies we're detecting are incredibly subtle variations in the expansion rate on the order of a few %, not a universe violently ripping itself to shreds. The fabric of space-time isn't being torn, it's being stretched with a gentle, albeit uneven, pressure. Our galaxy, our solar system, and even the atoms that make us up remain completely secure, held together by forces that are astronomically stronger than this large-scale cosmic tug. The real story isn't one of imminent destruction, but of a slow, majestic evolution over billions of years, a process that is more about mapping the gentle hills and valleys of the cosmos than it is about surviving a catastrophic rupture. This isn't to say that the genuine excitement isn't warranted, it absolutely is. The potential discovery that the universe's expansion is not uniform is a monumental shift in our understanding, a paradigm-level event that could rewrite the textbooks. The key is to channel the excitement toward the awe of the discovery itself, not toward a fictionalized doomsday scenario. The true crisis isn't happening out in the cosmos. It's happening here on Earth in the world of theoretical physics, where our best models are being stress-tested by stubborn data. This is the kind of crisis scientists live for, a puzzle that forces us to think bigger, to question our foundational assumptions, and to potentially uncover a deeper layer of reality. It's the crisis that preceded every great leap in human knowledge, from the dawn of quantum mechanics to the theory of relativity. Framing it as a constructive, intellectual challenge rather than an apocalyptic threat is not only more accurate, it's ultimately more inspiring. It invites viewers to be a part of the detective story, to appreciate the meticulous work being done to solve one of nature's greatest mysteries, rather than to simply fear an outcome that will never affect their daily lives. This places a tremendous responsibility on the shoulders of everyone communicating science, from journalists and documentary filmmakers to educators and content creators like myself. Accuracy in science communication is not about dumbing things down. It's about building up. It's about providing the necessary context and clarity so that people can appreciate the true significance of a finding without being misled by hyperbole. When we exaggerate, we erode public trust. If someone is told repeatedly that the universe is in a crisis, and then they look up at a perfectly stable night sky year after year, they may begin to dismiss all scientific warnings, including the very real and pressing ones we face here on our planet, like climate change. Conversely, when we communicate with care and precision, we empower people. We give them the tools to distinguish between sensational speculation and evidence-based discovery, to engage with science critically, and to share in the genuine wonder of what we're learning about our spectacular and beautifully complex universe. So where does this leave us after this grand tour from the quantum foam to the cosmic web? We have not one, but a whole tapestry of interwoven explanations, each thread strengthening our understanding while reminding us that the complete picture is still coming into focus. The uneven expansion of the universe isn't a problem with a single, simple solution. It is the emergent result of a spectacular cosmic conspiracy, a collaboration of forces and histories working across nearly 14 billion years. The mysterious push of dark energy acts as the primary accelerator, but its effect is dramatically modulated by the invisible gravitational scaffolding of dark matter, which itself was shaped by the random quantum seeds planted during a hyper-fast inflationary epoch. That primordial randomness was then amplified over eons by gravity, creating the vast cosmic voids where expansion runs wild and the dense clusters where it is held firmly in check. This grand synthesis shows us that these ideas are not competitors. They are partners in a single, magnificent story. Cosmic inflation explains the origin of the initial imperfections. Dark matter dictates where the structures formed, creating the gravitational landscape, and dark energy provides the accelerating force that acts upon that landscape, expanding the empty deserts rapidly while making little headway against the mountainous galaxy clusters. The multiverse hypothesis offers a breathtakingly vast framework in which our particular universe's combination of forces and irregularities could be just one random draw from a cosmic lottery. And the anthropic principle provides a philosophical lens through which to ask why we find ourselves in a universe with just the right amount of lumpiness to allow for our existence. No single theory holds all the answers because the phenomenon itself is not singular. It is a symphony with each section, the quantum, the gravitational, the energetic playing its essential part. This interconnectedness is the true beauty of the scientific endeavor. The mystery of non-uniform expansion is not a sign of failure, it is the engine of discovery. It is the persistent anomaly that forces us to look deeper, to build better telescopes, to run more sophisticated simulations, and to question our most fundamental assumptions. It drives the creation of missions like Euclid and the Vera C. Rubin Observatory, pushing our technological and intellectual boundaries. This ongoing quest reminds us that science is not a static collection of facts, but a dynamic, self-correcting process of inquiry. We are weaving this cosmic tapestry together, one observation, one theory, one breakthrough at a time, and the fact that the final picture is not yet complete is what makes the journey so utterly compelling. So as we reach the end of our journey, what are we left with? We've traveled from the faint afterglow of the Big Bang to the accelerating emptiness of cosmic voids, and the picture that emerges is not one of simple, predictable order, but of a complex and dynamic cosmos full of texture and mystery. The expansion of our universe is not a single, uniform beat, but a symphony of different tempos conducted by the interplay of dark energy's push, dark matter's pull, and the enduring legacy of quantum fluctuations from the first moments of time. This isn't a flaw in the cosmic design. It is the design itself, a reality far richer and more interesting than we ever imagined. These discoveries force upon us the most profound questions about the nature of existence itself. Are the variations we see, the faster expanding voids, the stubborn Hubble tension, the whispers of a dipole anisotropy, simply the random outcomes of a universe born from quantum chance, a cosmic lottery ticket that happened to be a winner for life? Or could they be subtle hints of something more, the fingerprints of a deeper level of physics, or perhaps even a universe with a capacity for spontaneity and creativity woven into its fundamental fabric? The data doesn't give us an answer, but it gives us the freedom to wonder, to explore the boundary between what we can measure and what we can only feel in the face of such grandeur. This is why the work is so vital. Every new telescope, every space mission like Euclid and James Webb, every simulation run on a supercomputer is not just about collecting more data. It is about deepening our conversation with the universe, about listening more closely to its story so we can understand our own chapter within it. The pursuit of this knowledge for its own sake is one of the most noble and defining endeavors of our species. It reminds us that we are not just passive inhabitants of a finished world, but active participants in a great cosmic unfolding, equipped with the curiosity to decipher its codes. As Carl Sagan so beautifully put it, somewhere, something incredible is waiting to be known. That sense of wonder, that driving need to look up and ask why, is our greatest inheritance. It's what propels us forward, so keep that curiosity alive. Look up at the night sky and see not just points of light, but a dynamic, expanding, and breathtakingly uneven cosmos, filled with mysteries we are only beginning to grasp. I'd love to hear which part of this cosmic story resonated most with you. Was it the quantum origins, the mysterious push of dark energy, or the mind-bending possibility of a multiverse? Share your thoughts in the comments below. Let's keep this conversation going. If this journey sparked your curiosity, Please like this video and subscribe to the channel for more deep dives into the wonders of space and time. Thank you for joining me on this exploration. Until next time, keep looking.